Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight we're going to drift toward one of the strangest ideas in modern physics, a thing so quiet, so ever-present, and so easy to overlook that it surrounds you even now, while you are sitting, lying down, breathing, blinking, or perhaps already beginning to feel the day loosen its grip. We are talking about the Higgs field. Not just the Higgs boson, that famous particle that made headlines and gave newspapers the chance to use phrases like God particle, far more often than most physicists would have preferred, but the field behind it. The silent, invisible background that helps explain why many of the particles inside atoms have mass at all. Before we ease into it, let me ask you something simple. Where are you listening from tonight? And what kind of quiet is around you right now? Is it the hush of a late room, the soft noise of traffic outside, the faint hum of a heater, the small clicks and sighs of a house settling into the night? It is a fitting question, because the Higgs field is also a kind of quiet background. Not a sound, not a substance you can touch, not a mist floating through space, but something that is there even when everything seems empty. It is part of what empty space is like, and that is already a wonderfully strange place to begin. If you find this kind of slow walk through the universe soothing, or if it gives your mind something calm to hold as you settle down, I would be very grateful if you liked the video and subscribed. It helps this little corner of peaceful physics reach others who may also enjoy falling asleep somewhere between atoms, stars, and the deep questions that make the universe feel both enormous and oddly intimate. And now, with no need to rush and no exam waiting at the end, let us begin gently, with the invisible ocean that fills all of space. Imagine, just for a moment, a perfectly empty room. No furniture, no dust in a sunbeam, no air, no light, no ticking clock, no forgotten mug on a bedside table. Take away every object. Take away every atom, take away every stray particle passing through. In ordinary life, we would call that room empty. There is nothing in it, nothing to bump into, nothing to weigh, nothing to see. But in modern physics, emptiness is not as empty as it looks. The deeper we look, the more we find that space itself has properties. It can hold fields, it can fluctuate, it can carry possibilities. It is not a blank stage with the universe placed on top of it. It is more like the universe already has a quiet texture, even when the actors have all left the room. A field, in physics, is a way of saying that something has a value everywhere. That may sound dry, but the idea is very familiar. The air temperature in your room is a field of sorts. It may be warmer near a lamp, cooler near a window, but every place in the room has some temperature. A weather map showing wind across a country is also describing a field. At every point the wind has a direction and a strength. The magnetic field around a fridge magnet is another example. You do not see it directly, but sprinkle iron filings nearby, and suddenly the invisible becomes visible through what it does. The filings arrange themselves into curved patterns, revealing that the space around the magnet was not simply empty. Something was there, quietly shaping the motion of matter. The Higgs field is not exactly like temperature, wind, or magnetism, but those examples help us step toward it. It is a field that exists everywhere in the universe, not just near planets, not just inside atoms, not just in laboratories where physicists build enormous machines and use more cables than any sensible person would willingly untangle. Everywhere, in the room around you, in the space between Earth and the Moon, in the wide darkness between galaxies, in the tiny regions inside every atom. Wherever space exists, as far as we can tell, the Higgs field is there too. And this is where the story becomes odd. Most fields we meet in everyday physics are noticeable when something creates them. A magnet creates a magnetic field. An electric charge creates an electric field. A planet is associated with gravity. But the Higgs field is different because it has a non-zero presence, even in its lowest energy state. In plain language, even when you remove everything you can remove, the Higgs field does not fade away to nothing. It remains. Empty space is soaked in it, though not soaked in the way cloth is soaked with water. It is not wet. It is not thick. It is not something you could bottle, stir, scoop or splash. It is a condition of space itself. That quiet presence matters because many fundamental particles interact with the Higgs field, and through that interaction they behave as though they have mass. This is the part people often describe with a simple image. A particle moves through the Higgs field and the field gives it mass. That is not a terrible starting point, as long as we keep it gentle and careful. The Higgs field does not grab particles like syrup, and it does not slow them down by friction. If it worked like a sticky fluid, particles would lose energy as they moved, and the universe would be a very different place. Probably not one where you could make tea, build stars, or listen to sleepy physics. Instead, the interaction with the Higgs field becomes part of what a particle is. A particle that interacts strongly with the Higgs field has a larger mass. A particle that interacts weakly has a smaller mass. A particle that does not interact with it in this way, like the photon, remains massless. So when we say that the Higgs field gives matter weight, we have to add a small cozy correction. Weight and mass are related, but they are not the same. Weight depends on gravity. You weigh less on the moon than on Earth, because the moon pulls on you more weakly. Your mass, however, is much more basic. It is the measure of how much resistance your body has to being accelerated, how much inertia is built into the particles and systems that make you. The Higgs field helps explain the mass of certain fundamental particles. Gravity then acts on mass and energy, giving rise to what we call weight. So the Higgs field is not exactly the thing that makes you heavy on a bathroom scale. It is part of the deeper story of why many of the tiniest ingredients of you have mass in the first place. That distinction may sound small, but it opens a door. Because once we ask why things have mass, we're no longer asking an ordinary question. We're asking why the universe is not made only of weightless particles racing forever at the speed of light. We're asking why atoms can form, why matter can clump, why chemistry can happen, why stars can burn steadily, instead of the cosmos being a thin storm of particles with no resting place. The Higgs field is one of the reasons the universe has structure. It helps make the familiar world possible, though it is not the only source of mass. Most of the mass of protons and neutrons, which make up most of the mass in your body, comes from the energy of the strong force binding quarks together, not directly from the Higgs field. Still, without the Higgs field giving mass to quarks and electrons and certain force-carrying particles, the universe would not have the same atoms, the same chemistry, or the same calm possibility of a person wondering about physics at night. It is worth pausing over how strange this is. You're used to thinking of mass as something objects simply have. A stone has mass, a cup has mass, a cat walking across your keyboard at exactly the wrong moment has mass, and often a surprising sense of purpose. But physics tells us that mass is not always a simple built-in label. At the deepest level, some masses arise from relationships. A particle is what it is partly because of how it interacts with fields. The electron has its particular mass because of its relationship with the Higgs field. Change that relationship and the electron would not be the electron we know. It would belong to a different kind of universe. This may feel less like machinery, and more like a rule in the background of existence. The Higgs field is not made of little beads spread through space. It is not a dust. It is not a hidden gas. It is a quantum field, which means that in the language of modern physics, it is one of the basic ingredients out of which particle behavior emerges. A particle is often described as an excitation of a field. That sounds technical, but there is a simple way to picture it without taking the picture too literally. Think of a calm surface of water. The water is the field. A ripple is not a separate thing made from some other material. It is the water moving in a particular way. In quantum field theory, particles are something like ripples in fields, though the real mathematics is much more precise and much less likely to get your socks wet. The electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. The Higgs boson is an excitation of the Higgs field. This is why the discovery of the Higgs boson mattered so much. Scientists did not scoop up a piece of the Higgs field and place it in a jar. They created conditions energetic enough to disturb the field in a detectable way, producing a Higgs boson, a brief ripple that quickly decayed into other particles. Finding that ripple was evidence that the field itself was real, or at least that the theory describing it was pointing to something physically present. It was like hearing a faint note from an instrument hidden behind a wall. You still do not see the instrument directly, but the sound tells you it is there. The field itself is calmer than its boson. The boson is the detectable disturbance. The field is the underlying presence. In daily life, you never notice it because it is everywhere and steady. A fish might not notice water if the water were perfectly still and had always been there. A person does not notice air pressure until climbing a mountain or opening a sealed jar. In the same way, the Higgs field does not announce itself in ordinary experience. It does not glow in the dark. It does not tug at your sleeve. It simply helps set the properties of particles, and those properties help build the world. This brings us closer to the question in the title. What is the Higgs field really made of? At first, the answer sounds almost disappointing. In the standard model of particle physics, the Higgs field is not made of smaller known pieces. It is treated as fundamental. That means it is not explained as a collection of tinier objects, at least not within our best tested theory. It is one of the basic fields. Asking what it is made of may be like asking what the electron field is made of, or what the electromagnetic field is made of. The theory says these are not substances assembled from parts. They are part of the starting vocabulary of nature. But that answer is not the end of curiosity. It is the beginning of a deeper kind. Whenever physics calls something fundamental, it is making a claim based on what we currently know and can test. Long ago, atoms were thought to be indivisible. Then we found electrons and nuclei, then protons and neutrons, then quarks and gluons. Nature has often hidden layers beneath layers. So when we say the Higgs field appears fundamental, we do not mean no deeper story can exist. We mean that so far, experiments have not shown us a smaller mechanism underneath it. The Higgs field behaves, within current measurements, like a basic field spread through the universe. The difficulty is that the Higgs field sits in a strangely sensitive place in our theories. It is necessary for the standard model to work as it does, but it also raises questions that make physicists shift in their chairs. Why does the Higgs field have the strength it has? Why does it settle into the value it has throughout space? Why is the Higgs boson mass what it is? Why is the field stable enough for the universe to exist in its present form? These are not small questions. They suggest that the Higgs may be a doorway rather than a final wall. It may be fundamental, or it may be a signpost pointing to something more hidden. For now, though, we can stay with the basic picture. The universe is filled with fields. Some fields produce the particles of matter. Some fields are associated with forces. The Higgs field is unusual because its constant background value changes the behavior of other fields and particles. It does not create all mass, but it gives mass to elementary particles such as electrons and quarks, and to the particles that carry the weak nuclear force. Without it, the weak force would behave very differently. Electrons would not have their familiar mass, and atoms as we know them would not hold together in the same way. The world would not simply be lighter, it would be rearranged at the deepest level. There is a calm wonder in that. Your hand resting on a blanket, the slow movement of your breathing, the atoms in the walls, the warm matter of stars far away, all of it depends on invisible rules that do not resemble the objects they create. The Higgs field is not a tiny brick inside matter. It is not hidden inside particles like a seed in a fruit. It is more like a universal condition that particles respond to. The electron is light because of one kind of response. The top quark is heavy because of another. The photon remains without mass because it does not take part in that interaction in the same way. Nature has arranged a subtle set of relationships, And from those relationships come atoms, chemistry, planets, and eventually someone lying awake just long enough to wonder what anything is made of. The word field can feel too ordinary for such a strange idea. A field is where cows stand, where wheat grows, where children kick footballs until the ball disappears into a hedge. But in physics, a field is something more general and far more powerful. It is a piece of reality assigned to every point in space and time. It can store energy, it can ripple, it can interact, it can make particles possible. And in the case of the Higgs field, it can quietly decide that some particles will not move through the universe as massless flashes, but as things with rest, inertia, and a slower pace. That slower pace matters. It gives the universe time to assemble complexity. In a universe without the Higgs field, or with a Higgs field very different from ours, the familiar story of matter might never get started. Electrons might move too differently to form atoms. The balance of forces inside stars might change. The delicate machinery of radioactive processes, nuclear reactions, and chemical bonding could be altered beyond recognition. This does not mean the universe was designed like a clock by someone adjusting dials in a workshop. It means our universe has certain parameters, and the Higgs field is among the important ones. Physics tries to understand why those parameters have the values they do. Sometimes it succeeds, sometimes it finds a deeper theory, sometimes it finds a mystery wearing a slightly better name badge. The Higgs field also teaches us something about how science progresses. It was not discovered by someone looking through a telescope and spotting a glowing haze between galaxies. It was inferred, predicted, searched for, and finally tested through incredibly careful experiments. Physicists noticed that the mathematics describing particles and forces had a problem. Certain particles needed mass, but simply adding mass by hand would spoil the structure of the theory. The Higgs mechanism offered a way for particles to acquire mass, while preserving the deeper consistency of the model. It was not invented as decoration. It was a solution to a real problem. Then came the long work of seeing whether nature had actually chosen that solution. That search took decades. It required accelerators, detectors, international collaborations, enormous patience, and the ability to find rare signals inside oceans of data. The Higgs boson itself lives for an extremely short time. It appears and vanishes, leaving behind other particles that must be reconstructed like clues at a very tiny crime scene, though perhaps a crime scene where the detective needs advanced statistics and a very large underground ring. When the evidence finally became strong enough, it confirmed that the Higgs field was not just a clever mathematical trick. Something corresponding to it was woven into the physical world. And yet, after all that, the field remains invisible in the ordinary sense. It is not less real because of that. Most of reality is not available directly to the senses. You do not see radio waves crossing the room. You do not feel neutrinos passing through your body by the trillions. You do not watch the strong force binding atomic nuclei. Science has repeatedly shown that the world we directly experience is only a small, human-sized surface laid over a deeper structure. The Higgs field belongs to that deeper structure. It is not mystical, it is not magic, it is a tested part of a scientific theory, but it is still wonderfully difficult to picture because our brains evolved to deal with fruit, weather, faces, and the occasional suspicious rustle in the grass, not quantum fields filling all of space. So we begin with a simple but unsettling idea. Empty space is not empty. It contains the Higgs field. Many particles are massive because they interact with that field. The field itself, as far as present experiments show, is not made of smaller known parts. It is treated as fundamental, though physicists continue to ask whether something deeper may be hiding underneath. The Higgs boson is the ripple that revealed the field. The field is the quiet presence that helps shape the matter in you, around you, and across the visible universe. As your thoughts settle into this, there is no need to force the picture to be perfect. Even physicists use different images depending on what part of the idea they are explaining. An ocean is helpful, but only partly. A background is helpful, but only partly. A field of values everywhere in space is closer, though less cozy. The important thing is that the Higgs field is not an object sitting somewhere. It is not located in one place. It is part of the way space behaves. It is one of the hidden features of the universe that makes familiar matter possible. From there, the next question comes naturally, slowly, almost by itself. If fields are so basic, and if particles can be understood as excitations of fields, then perhaps matter is not made of little solid pellets after all. Perhaps the deeper story is not about tiny billiard balls moving through emptiness, but about fields interacting, vibrating, and giving rise to the particles we name. To understand the Higgs field more clearly, we need to look at why particles needed such a field in the first place, and why mass, something that feels so obvious in everyday life, became such a difficult problem at the foundations of physics. To see why particles need a field to become themselves, we have to loosen one of the most stubborn pictures our minds like to keep. We often imagine the tiny world as if it were made of little hard grains, miniature specks with sharp edges, each one carrying its own built-in properties the way a pebble carries its shape. In that picture, an electron is a tiny bead called an electron. A quark is a tiny bead called a quark. A photon is a tiny bead of light, though if you tried to picture that too closely it would probably become a very stressed bead. This image is comforting because it resembles the ordinary world. A table is made of wood, a wall is made of bricks, a beach is made of sand. So perhaps matter is made of smaller sand, and smaller sand beneath that, all the way down. Modern physics asks us to set that picture aside, not because it is silly, but because it stops working when we look deeply enough. The smallest known particles are not little solid balls drifting through empty space. They are better understood as disturbances in fields. The fields are the more basic things. The particle is what happens when a field is excited in a particular way. This is not just a change in wording, it changes the whole story of what matter is. A particle is not an isolated object carrying every feature privately inside itself. It is an event in a field, a stable packet of behaviour, a ripple that can move, interact, and be detected. Think of a guitar string, but gently, because every analogy has a point where it starts wearing the wrong shoes. The string can vibrate in different ways. You hear a note, but the note is not a separate object glued onto the string. It is the string behaving in a certain pattern. If the string were perfectly still, there would be no note. In quantum field theory, each kind of particle is associated with its own field. The electron field can produce electrons. The quark fields can produce quarks. The electromagnetic field can produce photons. These particles are not made by scooping bits out of the field like spoonfuls of pudding. They are excitations, patterns, quantized disturbances that appear with specific properties. This means that when we ask what a particle is, we're also asking what field it belongs to and how that field behaves. A particle becomes recognizable because its field has rules. It has allowed ways of being excited. It has allowed ways of interacting. It carries certain properties through those rules. Charge, spin, mass, and other features are not just labels stuck onto a tiny object. They arise from the structure of the fields and their relationships with other fields. The universe at this level is not a collection of little parts sitting in a box. It is more like a network of fields, always present, capable of forming the particles we observe when energy is arranged in the right way. That is where the Higgs field enters, quietly but importantly. The particles of the standard model do not become the familiar particles we know merely by existing as fields. Some of them need the background presence of the Higgs field to have the masses they actually have. Without it, the electron field would not produce electrons with the same mass. Quark fields would not produce quarks with the same masses. The particles that carry the weak nuclear force would not have the heavy character that makes the weak force so short-ranged. The whole identity of many particles depends on how they relate to the Higgs field. This can sound as if the Higgs field is a kind of cosmic costume department, handing out outfits to particles as they pass by. The electron receives a light coat. The top quark receives a very heavy coat. The photon politely declines and leaves as it came. That is a friendly image, and it carries a little truth, but it can mislead if we take it too literally. Particles are not born naked and then dressed by the Higgs field after the fact. The relationship with the Higgs field is built into what the particle is in our universe. The electron is not first a massless electron that later picks up mass like dust on a shelf. The electron as we encounter it is already the result of the electron field existing in a universe where the Higgs field has its particular background value. This is why the phrase "become themselves" is useful. It does not mean particles are waiting in a queue to receive identities. It means the recognizable particles of our world are shaped by the fields around them and by the rules connecting those fields. In the deepest description we currently have, a particle is not self-contained. It is relational. It is defined partly by what it can interact with, how strongly it interacts, and what remains unchanged when those interactions happen. The Higgs field is one of the relationships that turns the mathematical ingredients of the theory into the particle zoo we actually measure. The need for such a field came from a problem. In the middle of the 20th century, physicists were building a theory to describe fundamental particles and forces with great precision. They had learned that symmetry was not just a matter of pretty shapes, it was a guiding principle of nature. A symmetry in physics means that something can be changed in a certain way, while the deeper rules remain the same. That may sound like a quiet idea, but it is powerful. Symmetries help determine which interactions are allowed. They help keep theories consistent. They help prevent the mathematics from falling apart when pushed to high energies. The electromagnetic force, for example, fits beautifully into this kind of thinking. Its symmetry structure gives rise to the photon, the particle associated with light and electromagnetism. The photon has no mass, and that fits the theory very naturally. A massless photon means electromagnetism can reach across long distances. A magnet can affect a compass. Light from a star can cross space. Radio signals can travel from towers, satellites, and the occasional device that refuses to connect until you restart it. The weak nuclear force was harder. It is responsible for certain forms of radioactive decay and important reactions inside stars. Unlike electromagnetism, it acts only over incredibly tiny distances. The particles associated with the weak force are heavy. That heaviness explains why the weak force is so short-ranged. But simply putting heavy force particles into the theory by hand caused trouble. It broke the very symmetry principles that made the theory work. It was like trying to repair a delicate clock by pressing a brick into the gears. You could make one feature look right, but the deeper mechanism would no longer run properly. Physicists needed a way for certain particles to behave as massive while preserving the underlying structure of the theory. This is the key. The Higgs field was not introduced because someone thought it would be charming to fill empty space with a mysterious invisible presence. It was introduced because the theory needed a lawful way for mass to appear. The particles could not simply be assigned mass carelessly without damaging the consistency of the whole framework. The Higgs mechanism offered a solution. It allowed mass to arise from interaction with a field whose background presence changes the behavior of particles while keeping the deeper rules intact. There is a useful everyday comparison, though again it must be handled with care. Imagine a room full of people spread evenly across the floor. If nobody important enters, people remain where they are, chatting quietly. Now imagine someone well-known walks in. The crowd gathers around that person, and moving through the room becomes harder. From the outside, it might look as if the person has become more massive, not because their body changed, but because their interaction with the room changed the way they move. This old analogy is often used for the Higgs field. It gives a quick feeling for how interaction can change behaviour. But the real Higgs field is not a crowd, and particles are not celebrities trying to reach the snacks. The important idea is that a background field can affect how particles act without being a material substance in the ordinary sense. Another way to approach it is through inertia. Mass is not just about how strongly gravity pulls on something. Mass is also about resistance to changes in motion. A massless particle cannot sit still. It must move at the speed of light. A massive particle can be at rest relative to you. It can move slowly. It can form bound structures. It can be part of atoms. The Higgs field helps explain why electrons and quarks are not forced to behave like massless particles. It gives them the possibility of moving through the universe in the slower, more flexible way that allows matter to build complexity. This matters especially for electrons. Electrons are light, but their mass is essential. If electrons were massless, atoms would not behave as they do. The delicate arrangements of electrons around nuclei are what make chemistry possible. Chemistry is what makes molecules possible. Molecules are what make rocks, water, air, cells, blankets, and late-night cups of tea possible. The mass of the electron is not a decorative detail. It helps set the size and behavior of atoms. It helps determine how matter feels, how it bonds, how it stores energy, and how life can make use of stable structures. Quarks also get part of their mass from the Higgs field. Quarks are the constituents of protons and neutrons, though they are never found freely in ordinary conditions. Their masses matter. But here the story gains an extra twist. Most of the mass of protons and neutrons does not come directly from the Higgs field. It comes from the energy of the strong force, from the restless confinement of quarks and gluons inside these particles. This is a beautiful reminder that mass has more than one origin. The Higgs field is crucial, but it is not the only source of mass in the universe. Still, if quarks had no Higgs given masses at all, the behavior of protons, neutrons, and atomic nuclei would change in deep ways. The balance that allows familiar matter would not be the same. The weak force particles show the role of the Higgs field even more dramatically. They are heavy compared with many other fundamental particles, and because they are heavy, the weak force acts over a very short range. That short range shapes how radioactive decay works. It shapes processes in stars. It shapes the early universe. The Higgs field is therefore tied not only to the identity of individual particles, but to the character of an entire force. The weak force becomes weak at everyday distances, partly because its carriers are massive, and they are massive because of their relationship with the Higgs field. So particles need a field to become themselves, because their properties are not isolated facts. They are outcomes of a field-based universe. The Higgs field does not sit outside the standard model like a helpful assistant brought in after the main work is done. It is woven into the way the electroweak theory works. It helps separate the electromagnetic force from the weak force in the universe we now inhabit. At very high energies, such as those present in the early universe, these forces can be understood as more closely unified. As the universe cooled, the Higgs field settled into its present background state, and the particles and forces took on the forms we observe now. This is one of the most important ideas in the whole story. The universe did not always have the same conditions it has today. In its earliest moments, it was extremely hot and dense. The fields were present, but the state of the universe was different. As cooling occurred, the Higgs field took on its non-zero background value. This was not like a fog rolling in from one side of space. It was a change in the state of the field throughout the universe. Once that happened, particles that interact with the Higgs field acquired the masses associated with those interactions. The universe changed phase in a sense, as water changes its behavior when it freezes or boils, though the physics involved is far more fundamental and not something you would want to test with a kitchen thermometer. A phase change is a helpful image because it shows how a system can have the same underlying ingredients while behaving in a new way. Liquid water and ice are made of the same molecules, but their large-scale properties differ because the molecules arrange and move differently. With the Higgs field, the shift is not about molecules arranging themselves, it is about the field settling into a state that changes the behavior of other fields. The laws did not vanish and reappear. The universe moved into a condition where particles became the massive particles familiar to the later cosmos. This also helps explain why mass is not merely an object property in the old-fashioned sense. The mass of a fundamental particle is tied to the vacuum state, the lowest energy condition of the fields. Vacuum here does not mean empty nothing. It means the field state that remains when particles are absent. The Higgs field has a background value in that vacuum. A particle moving through what we call empty space is therefore moving through a universe where the Higgs field is already present. Its mass reflects that relationship. It is natural to wonder why different particles interact with the Higgs field by different amounts. Why is the electron light while the top quark is so heavy? Why do neutrinos have tiny masses that are not fully explained in the simplest version of this story? Why do the strengths of these interactions have the values they do? These questions remain among the deepest puzzles in particle physics. The Higgs mechanism tells us how particles can acquire mass without wrecking the structure of the theory. It does not fully explain why each particle gets exactly the mass it gets. It gives the method, not the whole reason behind every number. Nature often answers one question by opening several more doors, which is very on brand for nature. This is also why the Higgs field feels both successful and unfinished. It solved a major problem. It predicted a particle, the Higgs boson, which was later found. It fits extremely well with many measurements, and yet it leaves us wondering whether the pattern of particle masses is pointing towards something deeper. There may be more fields, there may be additional symmetries, there may be mechanisms not yet discovered, or the masses may simply be parameters of our universe, facts we can measure but not yet derive from a deeper principle. Physicists do not know the full answer, and that uncertainty is not a weakness. It is the honest edge of the map. For the listener drifting near sleep, the essential idea can be kept simple. Particles are not tiny sealed containers of properties. They arise from fields. The Higgs field is one of those fields, and because it has a constant presence throughout space, it changes the way many other fields produce particles. Electrons, quarks, and weak force particles have their familiar masses because they interact with it. A particle becomes itself not in isolation, but through its place in the field network of the universe. There is a quiet shift in perspective here. Instead of asking what tiny thing lies inside the electron, we ask what field gives rise to the electron. Instead of asking how mass was packed into a particle like flour into a sack, we ask how the particle interacts with the Higgs field. Instead of imagining matter as a pile of little solid bits, we begin to imagine the universe as fields speaking to fields, with particles appearing as the measurable words in that conversation. That is not poetry. It is simply a different physical picture, less familiar to human senses but far closer to what our best theories say. And because the Higgs field is everywhere, this relationship is not rare. It is happening in every piece of ordinary matter. Every electron in every atom of your body belongs to this story. Every quark inside every proton and neutron is tied to it, even though the bulk of the proton and neutron mass comes from another source. Every weak interaction that helps stars shine and particles decay depends on the same underlying framework. The Higgs field is not a distant cosmic decoration. It is part of the background that allows ordinary matter to have the character it has. The more carefully we think about it, the more mass stops feeling like a simple heaviness and starts looking like a doorway into the structure of reality. We use mass constantly in daily life without noticing. A mug resists being moved, a book presses into a table, a body settles into a mattress. These familiar experiences are built from several layers of physics. Some of that story belongs to gravity, some belongs to the binding energy inside protons and neutrons, some belongs to the Higgs field and the masses of elementary particles. The word mass seems small, but it is carrying a great deal of hidden machinery. That hidden machinery is why the next step is so important. Before going deeper into symmetry and the standard model, it helps to separate two words that everyday language often blends together. Mass and weight feel almost the same when you're standing on Earth holding a heavy bag, but in physics they are different ideas. The Higgs field is connected to mass at the fundamental particle level, while weight is what happens when gravity pulls on mass and energy. Untangling that difference makes the Higgs field clearer, because it shows what the field is actually doing and what it is not doing, even as every object around you continues to sit calmly in place, as if none of this invisible work were happening at all. Mass and weight are so often treated as the same thing in ordinary life that it can feel a little fussy to separate them. We step onto a bathroom scale and say we are measuring our weight. We pick up a suitcase and call it heavy. We compare a bag of flour with a bag of apples and say one has more mass or more weight, depending on how carefully we are speaking and how much coffee we have had. In everyday situations on Earth, this confusion is harmless enough. The ground pulls on everything around us in a familiar way, so objects with more mass usually also have more weight. A large stone feels harder to lift than a small stone. A full teapot feels more serious than an empty one. A sleeping dog becomes mysteriously immovable when it chooses the exact part of the sofa you wanted to sit on. But when we are trying to understand the Higgs field, the difference becomes important. The Higgs field is not mainly a story about why things feel heavy in your hand. It is a story about why certain fundamental particles have mass. Weight comes later, when gravity enters the scene. Mass is more basic. Weight is what happens when gravity pulls on something that has mass and energy. The two are related, but they are not identical, and if we blur them together too much, the Higgs field starts to sound like a magical heaviness generator, which it is not. Let us begin with the simplest everyday distinction. Mass is a measure of how much inertia something has. Inertia is the tendency of an object to resist changes in its motion. If something is sitting still, it tends to remain still unless something pushes or pulls it. If it is moving, it tends to keep moving unless something changes that motion. A more massive object is harder to speed up, slow down, or turn. You can feel this when pushing an empty shopping cart compared with a full one. The full cart does not merely weigh more because Earth is pulling on it. It is also harder to get moving, and harder to stop once it has started rolling toward a display of oranges with a confidence it did not ask permission for. This resistance to changes in motion would still matter even far from Earth, far from the moon, far from any planet. Imagine floating in deep space beside two objects, a tennis ball and a large metal safe. There may be almost no noticeable gravity from nearby worlds, so neither object has much weight in the ordinary sense. They can both float beside you, but they do not have the same mass. If you gently push the tennis ball, it moves away easily. If you push the safe, it barely responds, and you may end up drifting backward instead, feeling mildly betrayed by physics. The safe is not heavy there in the same way it is heavy on Earth, but it is still massive. It still resists being accelerated. That resistance is mass showing itself without weight. Weight, by contrast, depends on gravity. On Earth, your weight is the pull of Earth's gravity on you. On the Moon, the gravitational pull is weaker, so your weight would be lower. You could hop more easily, lift objects that would feel unmanageable on Earth, and perhaps briefly feel like a graceful astronaut before discovering that low gravity does not automatically improve coordination. But your mass would not have changed. The particles in your body would still have the same masses. Your inertia would still be there. If someone tried to push you sideways on the Moon, you would resist that change in motion according to your mass, even though the ground would pull on you less strongly. This is why the statement that the Higgs field gives particles weight is not quite right. It gives certain fundamental particles mass, or more carefully, it is part of the mechanism through which they have rest mass. Weight only appears when those particles are in a gravitational field. On Earth, gravity acts on the matter in your body, and the ground pushes back on your feet, and that combination is what you feel as weight. The Higgs field is far deeper in the story. It helps set the masses of electrons, quarks, and the heavy particles of the weak nuclear force. It does not press you downward into your mattress. Gravity does that. The mattress then presses upward, and your nerves report the whole arrangement as the familiar feeling of lying down. It is useful to notice that weight can disappear in situations where mass remains. Astronauts in orbit are often described as weightless. That word is good enough for ordinary speech, but the fuller picture is more interesting. They are not weightless because gravity has vanished. Earth's gravity still reaches the space station strongly enough to keep it in orbit. The astronauts feel weightless because they, the station, and everything inside are falling together around Earth. There is no floor pushing up on them in the usual way. A floating astronaut still has mass. A floating laptop still has mass. A floating drop of water still has mass, though it may choose to become a wobbling sphere and drift directly towards some expensive equipment. If you tried to shove a massive object in orbit, it would resist the push. Mass remains even when the sensation of the weight fades away. This distinction helps us avoid a common misunderstanding about the Higgs field. When people hear that the Higgs field gives mass to particles, they sometimes imagine it as a source of heaviness, as if every object is heavy because the Higgs field is somehow dragging on it. That image is tempting, but it leads the mind in the wrong direction. The Higgs field does not act like friction. It does not slow particles down as they move. It does not make them tired, sticky, or burdened. A particle with mass can still move freely through space. If nothing interacts with it, it keeps moving. Its mass means it cannot travel at the speed of light, and it has inertia. The Higgs field is not a resistance medium in the everyday sense. It is not cosmic syrup. A better way to think is that the Higgs field changes the underlying character of certain particles. Its constant background presence is built into their identity. An electron has its particular mass because the electron field is coupled to the Higgs field in a particular way. The top quark has a much larger mass because its coupling is much stronger. The photon remains massless because it does not acquire mass through this mechanism. The difference is not that one particle is swimming through thicker Higgs fluid than another. The difference is in the relationship between fields. The universe is not dragging these particles through a substance. It is defining them through interactions that exist everywhere. Now, when we move from individual particles to ordinary objects, the story becomes layered. A person, a planet, or a cup of tea is made of atoms. Atoms contain electrons and nuclei. Nuclei contain protons and neutrons. Protons and neutrons contain quarks and gluons, bound by the strong nuclear force. The Higgs field helps provide the masses of the electrons and quarks, but most of the mass of protons and neutrons comes from the energy of the strong force inside them. This is one of those facts that can quietly rearrange your sense of the world. Most of the mass in the ordinary matter around you is not simply the sum of quark masses handed out by the Higgs field. Much of it is energy locked into the restless dynamics of the strong force. This does not make the Higgs field less important. It means the Higgs field is important in a precise way. It gives mass to elementary particles such as quarks and electrons, and it gives mass to the weak force carriers. But the mass of a whole object comes from several sources. The quark masses matter. The electron masses matter. Binding energies matter. The energy inside protons and neutrons matters enormously. By the time you weigh a book on a scale, you are seeing the combined result of many layers of physics, all sitting calmly on your desk as if they were not a complicated agreement between quantum fields, nuclear forces, electromagnetism, and gravity. A scale does not directly measure the Higgs field. It measures force, usually the force with which the object presses on the scale under gravity. If you bring the same scale to the moon, it reads differently because gravity is weaker there. If you bring the object into orbit, the scale may read nothing in the usual way, because the object and scale fall together. The Higgs field has not changed in those places. The particles in the object still have their masses. What changed is the gravitational environment and the mechanical contact with the scale. That is why mass is not the same as weight, and why the Higgs field is a mass story, not a bathroom scale story. There is another subtle point here. Gravity does not only respond to mass in the simple everyday sense. In modern physics, gravity responds to energy and momentum as well. Light has no rest mass. yet it is affected by gravity. A beam of light passing near a massive star can bend. This was one of the great confirmations of Einstein's view of gravity. So even the word mass is not the whole gravitational story. But for ordinary objects moving slowly compared with light, mass is a very good way to describe how strongly they gravitate and how strongly they resist acceleration. In the calm world of tables, chairs, people, and sleeping cats, mass and weight stay closely connected because Earth is always pulling and we're usually not falling freely around the planet. This is where the Higgs field gives us a doorway into a deeper question. Why should any fundamental particle have rest mass at all? Why should an electron be able to sit still relative to us instead of always moving like light? Why should the weak force carriers be heavy? Why should different particles have different masses? These are not questions that everyday gravity can answer. Gravity tells us how masses attract and how objects move through curved space-time. It does not explain why the electron has its particular mass. For that, we need the Higgs field and the structure of the Standard Model. The Standard Model is the current framework describing known elementary particles and three of the fundamental interactions. It is not a theory of everything, and gravity is not included in it in the same way, but within its domain it is extraordinarily successful. In this framework, the Higgs field plays a special role. It allows particles to have mass without destroying the delicate symmetries that organise the theory. That may sound like a technical concern, but it is central. Without the Higgs mechanism, simply inserting masses into the theory would create serious problems. The Higgs field lets the universe have massive particles while preserving a deeper mathematical consistency. The result is that mass becomes less like a simple ingredient and more like a consequence of structure. The electron mass is not a tiny lump hidden inside the electron. It is a feature of how the electron field behaves in the presence of the Higgs field. The mass of the weak force carriers is tied to the way the Higgs field reshapes the electro-weak interaction. These particles become what they are because the vacuum itself, the lowest energy state of the fields, is not empty in the plain sense. It has the Higgs field value built into it. The word vacuum can be misleading because it makes us think of nothingness. A vacuum cleaner, despite its dramatic name, mostly contains air, dust, and occasionally a lost earring. A laboratory vacuum means much of the air has been removed, but fields remain. In quantum field theory, the vacuum is the lowest energy state of the fields, not the absence of all physical properties. The Higgs field has a non-zero value in that vacuum. This is why particles do not need to pass through a special region to acquire mass. The condition is everywhere. Every electron in your body exists in that background. Every quark inside every atomic nucleus exists in that background. It is not a place particles visit. It is the state of the universe they inhabit. Now, because mass is connected to inertia, the Higgs field is connected to the fact that many particles do not behave like light. A massless particle, such as a photon, always moves at the speed of light in empty space. It cannot be brought to rest. A massive particle can move at many speeds below the speed of light. It can be slow. It can be trapped in an atom. It can be part of a stable structure. This difference is essential for the world. If electrons were massless, atoms would be radically different. If the particles of the weak force were massless, the weak force would not be short-ranged in the way we observe. If quark masses were very different, the balance of nuclear matter could change. The Higgs field helps make the universe a place where matter can settle into forms instead of everything behaving like radiation. The quiet difference between mass and weight therefore protects us from giving the Higgs field the wrong job. The Higgs field does not explain why you weigh less on the moon. It does not explain why a falling elevator makes people feel temporarily weightless. It does not explain why your suitcase seems to gain weight on the final staircase after a long trip, though tired arms may have their own strong opinions. The Higgs field explains why certain elementary particles have mass at all. Gravity then acts on the matter made from those particles and from the energies that bind them together. Weight is a later chapter in the chain of causes. Mass sits deeper. There is a neat way to feel this distinction with an imaginary experiment. Suppose you are in a spacecraft far from any planet, with two sealed boxes floating in front of you. One box contains a feather, the other contains a dense metal block. There is no floor, no scale, no obvious weight. Both boxes float. If you only looked at them, you might not know which contains more mass, but if you push them, the difference would reveal itself. The feather box would accelerate more easily, the metal box would resist. That resistance is not weight, it is mass. Now suppose the spacecraft lands on Earth. The metal box presses harder against the floor and is harder to lift. That is weight appearing because gravity is pulling on mass. Same object, same mass, different environment, different weight. The Higgs field belongs to the first part of that experiment, not the second. It is connected to the inertia built into elementary particles. It helps determine why they resist acceleration in the ways they do. It helps make it possible for objects to have mass before any particular planet pulls on them. This is why mass is more universal than weight. Your weight depends on where you are. Your mass is a property you carry with you, at least under ordinary conditions, because the Higgs field and other sources of mass are part of the structure of matter itself. There are, of course, deeper complications. In relativity, mass and energy are connected. A hot object has slightly more mass than the same object when cold because it contains more energy, though the difference is tiny in everyday life. A bound system can have a mass that reflects the energies and interactions inside it. The mass of a proton is largely the result of internal energy. These details remind us again that mass is not just a pile of tiny weights. It is a way energy and fields present themselves as inertia and gravitational influence. Still, the Higgs field remains central to the rest masses of elementary particles in the Standard Model. This also explains why the Higgs boson discovery was not simply the discovery of a particle that makes things heavy. It was evidence for the field whose background presence gives the Standard Model its mass-generating mechanism. The boson was a ripple in that field. The ripple was brief, unstable, and detectable only through its decay products in high-energy experiments. The field is the more important background feature. Saying the Higgs boson gives things mass is a common shortcut, but it's not quite accurate. The Higgs boson is not flying around inside matter, sprinkling mass onto particles. The Higgs field, in its steady vacuum state, is what matters for particle masses. In ordinary conversation, shortcuts are allowed. Physics would be exhausting if every sentence came with a polite warning label. But when we are trying to understand what the Higgs field really is, precision helps. The Higgs field is not weight, it is not gravity, it is not the same as the strong force energy that makes up much of the mass of protons and neutrons. It is a fundamental field with a non-zero value throughout space, and the coupling of certain particles to that field gives them rest mass. That is the cleaner version, though perhaps less likely to fit on a mug. Once this distinction settles, the everyday world becomes a little stranger in a useful way. A stone feels heavy in your hand because Earth pulls on it, and your hand must push back. But the stone has mass because its internal matter resists changes in motion, and that mass comes from a mixture of Higgs-related particle masses and the energy of strong interactions inside nuclei. The stone is not simple, it is a compact agreement between fields. The same is true of your hand. The same is true of the air, the floor, the walls, and the distant moon that would make the stone weigh less without changing its mass. Even rest becomes interesting. When an object sits still on a table, nothing looks dramatic. But the reason it can sit still at all is partly that it is made of massive particles. Massless particles do not sit still. Light does not rest on the table like a coin. It moves, reflects, absorbs, scatters. Matter can form stable objects because massive particles can arrange into bound systems with structure. The Higgs field helps provide that possibility at the elementary level. It gives some particles the capacity to be slow enough, in a sense, to join the architecture of matter. This is not to say the Higgs field alone builds atoms, Electromagnetism holds electrons to nuclei. The strong force holds nuclei together. Quantum mechanics sets the rules for atomic structure. Gravity gathers matter into planets and stars. The Higgs field is one member of a large cast, but it is a foundational one. It helps make the actors recognizable before the larger drama begins. Without it, the roles would be rewritten. So when we ask what the Higgs field is really made of, the difference between mass and weight keeps us pointed in the right direction. We are not looking for the origin of heaviness as felt by a hand. We are looking for the origin of rest mass for fundamental particles. We are looking at why some excitations of fields behave as massive particles while others do not. We are looking at the strange fact that empty space has a property that helps define the particles moving through it. That is subtler than weight, but far more fundamental. A quiet room at night may feel still, but at the level of physics it is full of structure. Fields are present. Electrons in atoms have mass. Quarks inside nuclei have masses and are bound by enormous internal energies. Photons from a lamp or screen move without rest mass. Gravity pulls on the room, the floor pushes back and everything feels settled. Beneath that settled feeling is the distinction we've been drawing. Weight is local and gravitational. Mass is deeper and inertial. The Higgs field helps explain part of mass, especially for elementary particles. It does not explain every gram in the same direct way, and it does not replace the other forces. It fits into a larger machine. That larger machine is where the story now needs to go. The Higgs field makes the most sense when placed inside the Standard Model, where particles are not isolated dots but members of a carefully arranged system of fields and interactions. There, the Higgs field is not an optional decoration. It is tied to the way the weak force works, the way symmetries are preserved and hidden, and the way the universe moved from an early high-energy state into the particle world we observe today. To understand why this invisible field was needed at all, we need to open that machinery slowly and see how the pieces fit together without losing the calm thread that brought us here. The machinery of the Standard Model is hidden not because it is secret, but because it is not built from the kinds of parts our senses were made to notice. You can take apart a clock and find gears, springs, screws and hands. You can open a radio and find circuits, wires, and components arranged in careful patterns. But if you could somehow open matter itself and look beneath atoms, beneath nuclei, beneath protons and neutrons, the pieces would not look like little clock parts. The deeper you go, the less the universe resembles a miniature version of the everyday world. It becomes a system of fields, rules, interactions, and symmetries. It becomes less like a pile of tiny objects and more like a set of instructions that can produce objects when energy moves through them in the right way. The Standard Model is the name physicists give to the best-tested description of the known elementary particles and most of the forces that act between them. It is not complete. It does not include gravity in the same way. It does not explain dark matter. It does not tell us why the universe contains more matter than antimatter. It does not fully explain neutrino masses. It leaves several numbers in place as measured facts, rather than deriving them from something deeper. So it is not the final answer to everything. But within the region where it works with astonishing accuracy. It is one of the most successful scientific frameworks humans have ever built, even if it has the unfortunate habit of sounding like a filing cabinet full of technical terms. At its core, the Standard Model sorts the known elementary particles into two broad kinds. There are matter particles, which make up the familiar stuff of the world, and there are force-carrying particles, which are associated with interactions between matter particles. The matter particles include quarks and leptons. Quarks are the ingredients of protons and neutrons. Leptons include the electron, which is essential for atoms and chemistry, along with heavier relatives and neutrinos. The force-carrying particles include the photon for electromagnetism, gluons for the strong nuclear force, and the heavy carriers of the weak nuclear force. Then there is the Higgs boson, which does not fit into the same everyday category as matter or ordinary force carrier. It is the ripple of the Higgs field, and that field is what gives the whole machine its subtle mass-generating mechanism. This sounds like a list of particles, but the list is only the visible surface. The deeper picture is that each particle comes from a field. The electron field exists everywhere. When it is excited in a particular way, we detect an electron. Quark fields exist everywhere. When they are excited, we detect quarks. The electromagnetic field exists everywhere. Its excitations are photons. In this way, the universe is not made of particles sitting inside empty space like beads in a jar. It is made of fields that fill space, and particles are the detectable excitations of those fields. The Standard Model is the rulebook for how these fields behave and how they interact. One of the remarkable features of this rulebook is that it is organized by symmetries. In ordinary language, symmetry often means that something looks the same after you rotate it, flip it, or reflect it. A snowflake has visible symmetry. A round plate looks the same if you turn it. A face has approximate symmetry, though usually not enough to survive a camera held too close. In physics, symmetry has a broader meaning. It means that you can change the description of a system in some specific way, and the physical predictions remain the same. These symmetries are not just decoration, they dictate the structure of the theory. They help determine which particles must exist, how they interact, and what kinds of behavior are allowed. This is where the Standard Model begins to feel less like a list and more like a machine. The force-carrying particles are not added randomly. They arise because the theory is built around certain symmetry requirements. When physicists demand that the rules remain consistent under those symmetries, the force fields appear naturally. The photon belongs to the structure of electromagnetism. The gluons belong to the structure of the strong force. The weak force carriers belong to the electroweak structure that connects electromagnetism and the weak force at a deeper level. It is as if insisting on a certain kind of balance in the rules forces the universe to include particular messengers. The strong force is the interaction that binds quarks together inside protons and neutrons, and binds protons and neutrons into atomic nuclei. It is carried by gluons, though the word carried should not make us imagine tiny delivery workers moving force parcels from one quark to another. Gluons are excitations of the strong field, and the interaction is a quantum field process. The strong force has an unusual character. It does not fade gently with distance in the way electromagnetism does. Quarks are confined, meaning we do not find isolated quarks wandering freely in ordinary conditions. Try to pull quarks apart and the energy in the strong field grows until new particles are produced. It is a little like trying to separate two ends of a rubber band and discovering that instead of getting one lonely end, the universe hands you more rubber bands. The analogy is not perfect, but the stubbornness is real. The strong force is also responsible for a major part of the mass of ordinary matter. Protons and neutrons are much heavier than the simple sum of the quark masses inside them. Most of their mass comes from the energy of the strong interaction, from the motion and binding of quarks and gluons in a confined system. This is why it would be wrong to say the Higgs field accounts directly for all the mass around us. The Higgs field gives masses to the elementary quarks, and those masses matter, but the strong force supplies most of the mass in the protons and neutrons that make up most of your body. So the Standard Model already teaches us that mass is not one thing with one origin. It is a layered result of fields, energy, and interactions. Electromagnetism is more familiar. It governs light, electric charge, magnetism, chemistry, and much of the structure of everyday matter. Electrons are held around atomic nuclei by electromagnetic attraction. The shapes of electron arrangements determine how atoms bond, how molecules form, why water behaves as it does, why metals conduct, and why your blanket does not let you fall through the bed even though atoms are mostly empty space by volume. The photon, the excitation of the electromagnetic field, is massless. Because it is massless, electromagnetic effects can extend over long distances. light from distant stars can cross the universe. Radio waves can carry voices and music. A charged object can influence another charged object across a gap. The weak nuclear force is less familiar in daily life, but it is deeply important. It is involved in radioactive decay and in processes that allow stars to shine. It can change one kind of particle into another. It plays a role in the nuclear reactions that build elements and in the subtle processes that shape the early universe. Unlike electromagnetism, the weak force acts over an extremely short range. The reason is that its force-carrying particles are massive. They are not light, long-reaching messengers like the photon. They are heavy, and that heaviness makes the weak interaction short-ranged. This was one of the great puzzles that led to the Higgs field. The electromagnetic force and the weak force are connected in a deeper electroweak theory. At high energies, they are understood as different aspects of a more unified structure. But in the world we inhabit, they look very different. Electromagnetism reaches far and is carried by a massless photon. The weak force reaches only tiny distances and is carried by massive particles. How can one underlying structure produce such different results without breaking the mathematical consistency of the theory? The answer involves the Higgs field. Before the Higgs field is included, the symmetry structure of the electroweak theory strongly prefers force-carrying particles that behave as massless. That is fine for the photon, but not for the weak force carriers we observe. Simply declaring those weak force carriers to be massive by hand causes serious problems. It damages the symmetry principles that make the theory reliable and predictive. The Higgs field solves this by allowing the underlying symmetry to remain present in the rules while becoming hidden in the state of the universe. The field settles into a non-zero background value, and through its interaction with the electroweak fields, some combinations become massive while one remains massless as the photon. This is often described as spontaneous symmetry breaking. The phrase sounds dramatic, almost as if the universe knocked over a vase and tried to look innocent. But the idea is more precise. The laws can possess a symmetry even when the particular state of the system does not display it openly. A simple example is a round table with a pencil standing upright in the exact centre. The table is symmetric in every horizontal direction. But if the pencil falls, it must fall in some particular direction. The underlying situation did not favour that direction in advance, but the final state does. The symmetry of the setup is hidden by the choice of state. With the Higgs field, the analogy is not exact, but it gives the right flavour. The laws retain their deep structure, while the vacuum state of the universe selects a particular condition that changes how particles behave. The word vacuum here deserves another careful pause. The vacuum in quantum field theory is not pure nothingness. It is the lowest energy state of the fields. It can have properties. The Higgs field has a non-zero value in the vacuum. That means empty space is not empty of Higgs field presence. This background value is the key to the Higgs mechanism. Particles that interact with the Higgs field do so everywhere, because the field is everywhere. Their masses arise from that constant relationship with the vacuum state. The matter particles receive mass through their own couplings to the Higgs field. Coupling is just the physicist's word for how strongly one field interacts with another. The electron has a small coupling to the Higgs field, and therefore a small mass. The top quark has a much larger coupling and therefore a much larger mass. Other particles fall into their own places. This pattern is measured, not fully explained. The standard model can accommodate these different couplings, but it does not tell us in a deep satisfying way why each one has exactly the value it has. It is like having a piano where every key works perfectly, but no one has yet explained why the keys were tuned to precisely those notes. The music is real. The pattern is still mysterious. Neutrinos add another complication. In the simplest original form of the standard model, neutrinos were massless. Experiments later showed that neutrinos change type as they travel, which implies that they have tiny masses. This discovery revealed that the standard model, in its simplest form, was incomplete. The Higgs field may be involved in neutrino mass in some extended way, but the full mechanism remains an open question. That matters because it reminds us that the Standard Model is not a closed book. It is a very accurate map with some edges still unfinished, and the Higgs field may be close to those edges. The Higgs boson enters as the visible ripple of the Higgs field. When scientists at the Large Hadron Collider smashed protons together at extremely high energies, they created conditions where the Higgs field could be excited in a detectable way. The Higgs boson itself decays almost immediately into other particles. Detectors do not catch it like a butterfly in a net. They reconstruct its presence from the patterns left behind by its decay. It is a very careful form of inference, repeated across enormous amounts of data. When the evidence became strong enough, physicists announced the discovery. That discovery confirmed the existence of something very close to the Higgs field predicted by the Standard Model. But the discovery did not end the story. It made the next question sharper. Is the Higgs boson exactly the particle predicted by the Standard Model? Does it interact with other particles in exactly the expected way? Are there additional Higgs, like particles? Is the Higgs field fundamental, or is it made from something deeper? Does it connect to dark matter? Does it reveal clues about why the universe did not collapse into a different vacuum state? These questions are still active. The Higgs boson was not a final full stop. It was a door opening into a room we are still slowly lighting. Inside the Standard Model, the Higgs field has a very specific role, but it also sits in a strange position. Other fields are associated with matter particles or forces. The Higgs field is different because it is a scalar field, meaning it has a value without a direction in space. A magnetic field has direction. At each point it points a certain way. The Higgs field is more like a number assigned to each point, though that word number should not make it sound simple. Its special nature makes it the first fundamental scalar field ever observed. That alone is remarkable. It suggests a kind of field that had long been possible in theory, but only became experimentally confirmed with the Higgs discovery. This raises a natural question. If the Higgs field is a scalar field, and if it fills the vacuum, could there be other scalar fields? Cosmology often uses scalar fields in theories of the early universe. Some ideas about inflation, the rapid expansion thought to have happened very early in cosmic history, involve scalar fields. Dark energy is sometimes modelled in ways that resemble field behaviour. None of this means the Higgs field is automatically the answer to those mysteries. It probably is not so simple. But the existence of the Higgs field shows that scalar fields are not merely mathematical decorations. Nature does seem to use at least one. The machinery also includes antimatter. For many matter particles, there is a corresponding antiparticle with opposite electric charge or other reversed properties. Electrons have positrons, quarks have antiquarks. When particles meet their antiparticles, they can annihilate into other forms of energy. The Standard Model handles antimatter naturally through its field structure, but it also leaves a major cosmic puzzle. The early universe should have produced matter and antimatter in nearly equal amounts, as far as simple expectations go. Yet the universe around us is overwhelmingly made of matter. The Standard Model contains some matter-antimatter asymmetry, but not enough to explain the observed universe. This is one of the clues that something beyond the Standard Model must exist. Then there is dark matter. Astronomical observations show that galaxies and galaxy clusters behave as if there is much more matter present than we can see. This dark matter does not appear to be made of ordinary atoms. The Standard Model does not contain a good dark matter particle. The Higgs field may provide a possible connection because some theories suggest dark matter could interact with ordinary matter through the Higgs field. This is sometimes called a Higgs portal in more technical discussions, though for our purposes it is enough to say that the Higgs field might be one of the few ways hidden matter could speak softly to known matter. So far, no such signal has been confirmed. The Standard Model is also silent about gravity in its usual form. Gravity is described beautifully by general relativity, where mass and energy curve space-time. The Standard Model is a quantum field theory built on a different framework. Both theories work extremely well in their own domains, but combining them into one complete quantum description of gravity remains unresolved. The Higgs field lives within the quantum field theory side of the story. It is affected by gravity in the sense that all energy and fields belong to the universe gravity describes, but it is not itself a solution to quantum gravity. It does not explain space-time. It helps explain particle masses. This is part of what makes the Standard Model feel like hidden machinery rather than a final foundation. It has gears that mesh beautifully, but the machine is mounted inside a larger structure we do not yet fully understand. It describes the known particles with great precision, but it does not explain why there are exactly 3 generations of matter particles. It includes the Higgs field, but does not explain why the Higgs field has its particular strength and stability. It handles forces except gravity, but the universe includes gravity everywhere. It predicts and organizes, but it also points beyond itself. Still, its success should not be understated. Every ordinary object around you is shaped by the interactions it describes. The electrons in atoms, the quarks in nuclei, the photons carrying light, the gluons binding quarks, the weak interactions involved in nuclear processes, and the Higgs field helping set elementary masses are all part of this framework. A quiet bedroom may not look like a particle physics experiment, but its matter is a working display of the Standard Model. The softness of a pillow comes from electromagnetic interactions between atoms. The stability of the atoms depends on quantum rules and particle masses. The nuclei inside those atoms depend on strong interactions. The radioactive processes in the wider world depend on weak interactions. The mass of elementary particles depends on the Higgs field. The familiar world is what the hidden machinery looks like when it's calm, cold, and arranged into large numbers of atoms. This is why understanding the Higgs field requires stepping inside the Standard Model, rather than treating it as a lonely mystery. The Higgs field was not added to explain why rocks fall, or why people feel heavy after dinner. It was added because the electroweak theory needed a consistent way to produce massive weak force carriers and massive matter particles while preserving the deeper structure of the theory. Once included, it became essential to the identity of many particles. It also predicted the Higgs boson, whose discovery showed that the mechanism was not merely clever bookkeeping. And yet, the question of what the Higgs field is made of remains open at the deeper level. In the Standard Model, it is treated as fundamental. It is not made of quarks, it is not made of electrons, it is not made of little pieces of ordinary matter, it is its own field. But because the Standard Model is incomplete, physicists continue to ask whether the Higgs is truly elementary, or whether it hides a deeper structure. Some theories imagine it as composite, built from more fundamental ingredients bound by unknown forces. Others connect it to supersymmetry, extra dimensions, or new physics at energies beyond what we have reached. These ideas are not confirmed, but they exist because the Higgs field looks both necessary and strangely delicate. One of the reasons physicists suspect there may be more to the Higgs story is that the Higgs boson mass seems sensitive to effects from very high-energy physics. In simple terms, the Higgs appears to need protection from becoming far heavier than it is. The Standard Model can accept the measured value, but many physicists find it puzzling. This is sometimes called a naturalness problem. The word naturalness here does not mean nature must obey our taste. It means that certain values seem surprisingly balanced, unless a deeper mechanism explains them. Perhaps there is such a mechanism. Perhaps our expectations are wrong. The Higgs field sits right in the middle of this debate. For a calm listener, the main thing is not to memorize the particle list. It is to feel the shape of the idea. The Standard Model is a field-based structure. Matter particles come from matter fields. Force-carrying particles come from force fields. Interactions are organized by symmetries. The Higgs field fills the vacuum with a non-zero background value. Through that value, particles acquire mass in a way that keeps the theory consistent. The Higgs boson is the ripple of that field, detected after decades of searching. The whole framework works extremely well, while still leaving clues that deeper physics may be waiting. This hidden machinery is not remote from you. It is not locked only inside accelerators or written only in the notebooks of theorists. It is operating in the atoms of your skin, the air in your lungs, the light reaching your eyes, and the matter of the bed or chair supporting you. Every object is a quiet surface expression of quantum fields obeying rules no human sense can directly picture. The Higgs field is one of those rules made physical. It does not shout. It does not move like a wind. It is simply part of the vacuum condition that lets the particle world take its familiar form. Once that machinery is in view, the next idea becomes easier to approach. The Higgs field matters because it changes how symmetry appears in the universe. The laws can be symmetric, while the world we observe is not obviously so. Forces that may be related at high energy can look different at low energy. Particles that would otherwise be massless can become massive. The vacuum itself can choose a state, and that choice can shape everything that follows. To see why this matters, we need to spend time with symmetry, broken symmetry, and the quiet moment when the universe settled into the form that allows matter as we know it. Symmetry is one of those ideas that sounds simple until physics gets hold of it and quietly turns it into a key for the whole universe. In daily life, symmetry usually means balance, a butterfly wing matching another wing, a snowflake repeating its delicate pattern, a round plate looking the same no matter how you turn it in your hands. We notice symmetry because our eyes like order. It feels tidy, pleasing, dependable. But in physics, symmetry means something deeper than visual neatness. It means that something can be changed in the way we describe a system. While the actual physical rules stay the same, the appearance may shift, the viewpoint may move, the labels may be rearranged, yet the underlying behavior remains unchanged. That kind of symmetry is not just pretty, it is powerful. A simple example is the idea that the laws of physics do not change because you move from one place to another. If you drop a small ball in your kitchen and then drop the same ball in a quiet field, the basic rule governing its fall is the same. The details may differ because of wind, floor, grass, or the unfortunate presence of a curious dog, but the law itself has not packed a suitcase and become something else. That sameness from place to place is a symmetry. Another example is that the laws of physics do not change from one day to the next. If nature behaved one way on Tuesday and another way on Friday for no reason at all, science would become less of a discipline and more of a weather report with panic. The reliability of natural laws is connected to symmetry in time. These symmetries are so familiar that we almost do not notice them. They are the quiet assumptions underneath every experiment. A physicist in Tokyo and a physicist in Warsaw can compare results because they trust that nature is not using local rules in one city and an entirely different rulebook in another. A laboratory can repeat a measurement because the laws are not expected to wander off during lunch. Symmetry gives physics its backbone. It lets us search for patterns that hold beyond one place, one moment, or one observer. But the symmetries that matter in particle physics are not always visible. They are internal symmetries. They do not involve turning a snowflake or moving a ball across a room. They involve changing the mathematical description of fields in ways that leave physical predictions untouched. This sounds abstract, but the consequences are very concrete. The forces and particles of the standard model are deeply shaped by these hidden symmetries. When physicists require the theory to respect certain symmetries, the structure of the interactions follows. The force fields are not simply added because someone needed more characters in the story. They arise because the symmetry demands them. This is one of the great lessons of 20th century physics. Nature seems to care about symmetry, not always in the sense of making everything look balanced, but in the sense of keeping the deep rules consistent under certain transformations. The photon, the carrier of electromagnetism, fits into this way of thinking. Gluons, which are associated with the strong force, also fit into it. The particles that carry the weak force fit too, but with a complication. The weak force carriers are massive, and mass does not enter easily into the kind of symmetry structure that physicists needed for the electroweak theory. The theory wanted symmetry. The observed world wanted massive particles. Something had to give, but not in a careless way. This is where broken symmetry enters, although the phrase can be misleading. Broken symmetry does not mean the laws are smashed. It does not mean nature made a mistake. It means that the underlying laws may possess a symmetry, while the particular state of the system does not display it openly. The rules can be symmetric even when the outcome chooses one possibility from many. That is a subtle idea, but it appears in ordinary life more often than we might think. Imagine a perfectly round dinner table. At each seat there is a napkin, a plate, a glass, and a spoon. Before anyone sits down, the table has a kind of rotational fairness. No direction is special. Now imagine someone places a single flower vase slightly toward one side. The table itself is still round, but the arrangement has chosen a direction. The symmetry of the original setup is no longer obvious in the final state. Nothing illegal happened. The table did not stop being round. The arrangement simply selected one option, and that selection hid the original balance. Or think about a pencil balanced perfectly on its tip. In principle, every direction around it is equally possible. There is no preferred way for it to fall, but in real life, it cannot remain balanced forever. A tiny disturbance, perhaps from air movement, vibration, or the universe clearing its throat, causes the pencil to fall in one particular direction. Once it has fallen, that direction becomes part of the story. The final state is not symmetric, even though the original situation was. The symmetry is not destroyed in the laws, it is hidden by the chosen outcome. The Higgs field works through a deeper and more precise version of this idea. In the early universe, when temperatures and energies were extremely high, the electroweak symmetry was not hidden in the same way it is now. The electromagnetic force and the weak force were aspects of a more unified electroweak interaction. The particles associated with these forces did not yet have the same separate identities they have in the cooler universe we inhabit. As the universe expanded and cooled, the Higgs field settled into its present background state. That settling changed how the symmetry appeared. The underlying structure of the theory remained, but the state of the vacuum no longer displayed the full symmetry openly. The phrase vacuum state may sound like nothingness choosing a mood, but in quantum field theory the vacuum is not empty nothing. It is the lowest energy condition of the fields. The Higgs field has a value in this vacuum, even when no Higgs bosons are present. That value is not a little object hidden in space. It is a condition of the field everywhere. Once the Higgs field settled into that condition, particles that interact with it acquired mass. The weak force carriers became massive. The photon remained massless. Electromagnetism became long-ranged, while the weak force became short-ranged. The universe chose a shape, not in the sense of picking a visible outline, but in the sense of settling into a field configuration that determined the world of particles and forces we now observe. A useful comparison is a landscape with a valley. If a ball sits at the top of a perfectly rounded hill, every direction downward may be equally possible. But the ball will not stay at the top if that position is unstable. It rolls down into some place in the surrounding valley. The hill itself may have perfect symmetry, but the ball ends up at one specific location. That location becomes its state. In the Higgs story, the field does not settle at a simple zero value. It settles into a non-zero vacuum value, like choosing a point in a valley rather than resting at the central peak. The analogy is imperfect, because the real Higgs field is not a ball, and the vacuum is not a literal landscape, but it helps show how a symmetric set of rules can lead to a state that no longer looks symmetric. This choice has consequences everywhere. The Higgs field is not something that turned on in one region and then spread like sunrise across a planet. the cooling of the early universe changed the state of the field throughout space. The result was a universe in which elementary particles acquired the masses associated with their interactions with the Higgs field. The electron became the light but massive particle needed for ordinary atoms. Quarks acquired their masses. The weak force carriers became heavy enough to make the weak interaction short-ranged. The universe did not simply gain mass as if someone poured it into a container. The fields reorganized into the pattern that makes familiar matter possible. This is why broken symmetry is not a side issue. It is central to why the universe has the particle identities it has. Without the Higgs field settling into its present state, the electroweak force would not have separated into the familiar electromagnetic and weak forces in the same way. The photon would not stand apart as the massless carrier of light and electromagnetism, while the weak force carriers became massive. The structure of atoms, stars, radioactive processes and chemistry would all be different. Broken symmetry is not merely a technical phrase. It is part of the reason the world has texture. The word broken still causes trouble, because it suggests damage. But symmetry breaking in physics often means the emergence of structure. A perfectly uniform situation can be less interesting than one where a choice has been made. Water freezing into ice is a good everyday example of a system choosing structure. Liquid water looks roughly the same in every direction on small human scales. As it freezes, molecules arrange into a crystalline pattern. The symmetry of the liquid gives way to the ordered structure of ice. The result is not a mistake. It is a new state with new properties. Similarly, when a magnet cools below a certain temperature, tiny magnetic orientations can align. Before alignment, no direction is special. Afterward, the magnet has a direction. The symmetry is hidden by the state the material has chosen. The early universe went through changes of state as it cooled. These were not exactly like water freezing in a tray, because we are dealing with fundamental fields rather than molecules, but the broad idea of a phase transition helps. At high energy, a field can behave one way. At lower energy, it can settle into another state. Once settled, the field changes the behavior of particles moving through the vacuum. The Higgs field is tied to such a transition. It helped turn a hot, more symmetric universe into the cooler universe, with distinct forces and massive particles. This also gives the vacuum a strange importance. In everyday thinking, empty space is the absence of things. In modern field theory, the vacuum is a physical state with properties. The Higgs field value is one of those properties. It is the same everywhere as far as we can tell, which is why the electron has the same mass here as it does in distant galaxies. If the Higgs field had different values in different regions of the universe, particle masses could vary, and chemistry might be different from place to place. That would make the cosmos a very uneven laboratory. Observations strongly suggest that the basic particle properties are consistent across the visible universe, so the Higgs field appears to provide a universal background. The phrase universe choosing a shape is not meant to suggest intention. The universe did not think about its options and decide that atoms sounded pleasant. It followed physical laws. But physical laws can allow multiple possible states, and the actual state matters. The Higgs field settled into one of the allowed vacuum configurations. That settling is what we describe as symmetry breaking. It is a choice in the physical sense, not a conscious one. Like a pencil falling left rather than right, the outcome becomes definite, and the world that follows is shaped by it. There is another important subtlety. The Higgs field does not break every symmetry. Some symmetries remain exact in the world we observe. Electromagnetism remains associated with a massless photon. Electric charge remains conserved. The strong force continues to behave according to its own symmetry structure. The Higgs mechanism hides part of the electroweak symmetry while leaving another part visible. This selective hiding is why the photon remains massless while the weak force carriers gain mass. It is not an all-purpose mass switch. It is a precise rearrangement within the electroweak theory. The mass of matter particles arises somewhat differently from the mass of the weak force carriers, though both depend on the Higgs field. Matter particles interact with the Higgs field through couplings. Different particles have different coupling strengths, which is why their masses differ. The electron couples weakly and is light. The top quark couples strongly and is heavy. The standard model includes these couplings, but it does not explain why the pattern is what it is. This is one of the places where the machinery works beautifully, while still leaving a deep question on the table. The Higgs field gives a mechanism for mass, but it does not fully explain the menu of masses. That menu is astonishingly varied. Some particles are extremely light, others are much heavier. Neutrinos are so light that their masses forced physicists to extend or revise the simplest original picture. The top quark is enormously heavy by particle standards. The electron is light enough to allow atoms of the size and structure we know. These values matter. If the electron mass were very different, atoms would differ. If quark masses were very different, protons and neutrons might behave differently. If the weak force carriers were not heavy, the weak interaction would extend farther and the universe would not work as it does. The Higgs field is therefore connected not merely to mass in general, but to the detailed architecture of the particle world. One reason physicists care so much about symmetry is that it allows them to build theories that remain well behaved at high energies. Without the Higgs mechanism, the electroweak theory would run into problems when particles interact at very high energies. Predictions would become inconsistent. The Higgs field repairs this by preserving the deeper gauge structure of the theory while allowing particles to have mass. That may sound like a bookkeeping trick, but nature seems to have used it. The discovery of the Higgs boson showed that the field associated with this mechanism is not just a human convenience. It corresponds to something real enough to ripple, decay, and leave measurable traces in detectors. There is a calming irony here. The Higgs field is often introduced as the thing that gives particles mass, but its deeper role is about symmetry. Mass is the visible consequence. Symmetry is the hidden reason the mechanism was needed. The field allows the universe to have massive particles without losing the consistency provided by the electroweak symmetry. It hides symmetry rather than simply erasing it. It lets the laws keep their elegant form while the vacuum state creates the uneven world we observe, where light travels freely across space and weak interactions happen only at tiny distances. This idea changes how we think about the early universe. The hot young universe was not just a smaller version of the present universe. Its fields were in different conditions. Particles did not necessarily have the same effective properties they do now. As the universe cooled, changes in field states altered the behaviour of matter and forces. The Higgs field settling into its vacuum value was one of those changes. It helped establish the difference between electromagnetic and weak interactions and gave elementary particles their masses. In that sense, the mass of the electron today is a fossil of a transition in the early universe. It is a present-day property rooted in cosmic history. The word fossil may sound odd for a particle property, but it captures something real. The universe remembers its early conditions through the state of its fields. We live inside the aftermath of transitions that happened when the cosmos was extremely young. The microwave background is one kind of relic from early times. The abundance of light elements is another. The Higgs field vacuum is not a relic in the same observational sense, but it is a present state established as the universe evolved. Every atom now exists inside that state. Every chemical bond depends on particle properties shaped by it. The early universe is not only far away in time, it is quietly present in the rules that allow matter to be matter. Broken symmetry also helps explain why physics can be both simple and complicated. The underlying rules may have a compact symmetry, but the world that emerges can be varied and rich. Think again of a round table. The symmetric table is simple, but once people sit down, plates move, glasses shift, conversations begin, someone claims the last piece of bread, and the actual arrangement becomes much more complicated. The simplicity has not vanished, It is just no longer obvious. In particle physics, symmetries can organize the laws, while the vacuum state and interactions produce the complexity we see. This is one of the reasons the Higgs field feels almost like a hinge between emptiness and structure. It is part of the vacuum, yet it shapes particles. It is invisible, yet its consequences are everywhere. It preserves something deep in the laws, yet it creates differences in the world. The field does not make matter by itself, but it allows matter particles and weak force particles to take on the properties needed for the later universe. Without it, the standard model would not describe our reality. Still, the Higgs field brings its own mysteries. Why did it settle into the value it has? Why is the Higgs boson mass what experiments measure? Why is the vacuum stable enough, or at least long-lived enough, for galaxies, stars, planets, and listeners to exist? Why do the couplings to different particles have such varied strengths? Symmetry explains the form of the mechanism, but not every detail of the numbers. This is where physicists begin to suspect that the Higgs field may be connected to deeper layers of nature. Perhaps another symmetry protects it. Perhaps it is not fundamental. Perhaps it is related to unknown particles or forces. Or perhaps the standard model is stranger and more self-contained than many expected. The known Higgs field is also unusual because it is a scalar field. It has a value at each point but no direction in space. Most familiar fields, such as electric and magnetic fields, have directional character. The Higgs field is different. Its scalar nature allows it to fill the vacuum without pointing somewhere, and thereby breaking the visible symmetry of space itself. If the Higgs field had a direction like a tiny arrow everywhere, empty space might have a preferred direction, and we would notice. Instead, the Higgs field can have a universal value while space still looks the same in every direction on large scales. That is part of why it can shape particle masses without making the universe obviously lopsided. This is a very delicate kind of presence. The Higgs field is everywhere, yet it does not mark a north or south. It changes particle identities, yet it does not slow them like a fluid. It breaks electro-weak symmetry, yet it leaves everyday space looking even and isotropic. It is a background that matters only through the rules of field interaction. Our senses are not built for such things. We evolved to notice moving animals, changing weather, ripe fruit, and whether a chair is already occupied. We did not evolve to notice a scalar field value in the vacuum. Physics extends our perception through experiments and mathematics, allowing us to infer what cannot be seen directly. The Large Hadron Collider provided the crucial evidence by detecting the Higgs boson, the ripple of the Higgs field. In the symmetry story, this ripple is not an optional extra. It is the physical excitation expected when the Higgs field exists. If the field fills space and can be disturbed, then under the right energetic conditions, a quantum of that disturbance should appear. The discovery showed that the mechanism involving the Higgs field was not merely a way to make the equations behave, it had a particle signature. The vacuum field could be shaken, and the shake could be measured through its decay products. That brings us close to the next step. If the Higgs boson is a ripple, then understanding it helps us understand the field. It is not the field itself, just as a wave is not the entire sea, but it carries information about the sea beneath it. Its mass, its lifetime, the ways it is produced, and the particles into which it decays all tell physicists how the Higgs field interacts with the rest of the standard model. The boson is a messenger from the hidden vacuum structure. It is brief, rare, and difficult to catch, but it lets scientists test whether the field behaves as expected. For now, the important point is that symmetry gives the standard model its shape, and broken symmetry gives our universe its particular form. The Higgs field is the agent of that hiding. It allows the laws to retain a deep electroweak symmetry, while the cooled vacuum state produces a world with massive weak force carriers, massive matter particles, and a massless photon. It is a quiet choice written into empty space. Not a conscious decision, not a visible shape, not a substance drifting between stars, but a field state that determines what particles can be. And once that state is in place, The universe can move forward into atoms, stars, chemistry, and all the complicated calm of ordinary matter, while the ripple of the field waits to tell its own story. The ripple of the Higgs field is where an invisible idea became something experiments could touch, not with fingers of course, and not with a microscope, but with evidence. The Higgs field itself is the quiet background. It is the steady presence woven into the vacuum, shaping the masses of many elementary particles without making any sound, light, or obvious disturbance in everyday life. The Higgs boson is different. It is what happens when that field is excited. It is a brief disturbance, a little raised note in a field that normally sits silently everywhere. If the field is the thing that fills space, the boson is the ripple that tells us the field can be shaken. This distinction matters because people often speak as if the Higgs boson is the thing that gives particles mass. That is close enough for a headline, but not close enough for a peaceful understanding. The boson is not sitting inside atoms handing out mass. It is not hidden in your body like a tiny engine. It is not buzzing around the universe sprinkling heaviness onto electrons and quarks. The mass-giving role belongs to the Higgs field in its steady background state. The boson is the detectable excitation of that field. It is the sign that the field exists and behaves as the theory predicts. A wave on the surface of the sea is not the whole sea, but if you had never seen the sea directly, the wave would be very good evidence that something deeper was there. Before the Higgs boson was detected, physicists had strong reasons to believe the Higgs field existed. The standard model needed it. The weak force needed an explanation for why its carriers were massive while the photon remained massless. Matter particles needed a consistent way to have mass without breaking the theory. The Higgs mechanism solved these problems with remarkable elegance, though physicists are always careful with elegance, because nature sometimes enjoys being untidy just to keep everyone awake. The theory also predicted that if the Higgs field existed, it should have its own particle excitation. That excitation would be the Higgs boson. So the search became clear in principle and extremely difficult in practice. Find the ripple and you confirm the field. The difficulty comes from the fact that the Higgs boson is not an ordinary particle that hangs around waiting to be found. It is unstable. Once produced, it vanishes almost immediately, changing into other particles. You do not observe it directly in the way you might see a planet through a telescope or a bird on a fence. You infer it from what it leaves behind. It is more like noticing that a quiet pond has been disturbed by studying the patterns spreading outward after the pebble is already sunk. The pebble is gone, but the ripples carry the story. To make a Higgs boson, physicists needed enormous energy concentrated into extremely small spaces. This is why the Large Hadron Collider was built. Deep beneath the border region of France and Switzerland, protons are accelerated around a vast circular tunnel until they move at nearly the speed of light. Then they are made to collide. The word collide may sound simple, like two billiard balls tapping together on a table, but protons are not smooth little balls. They're complicated bundles of quarks, gluons, and field energy. When protons collide at high energy, their internal ingredients can interact in many possible ways. Most collisions produce familiar sprays of particles. Very rarely the energy concentrates in just the right way to produce something heavy and short-lived, including a Higgs boson. Even then, the Higgs boson does not stay. It decays. It transforms into other particles according to the rules of quantum field theory. Detectors surrounding the collision point record the particles that fly outward. These detectors are enormous layered instruments, built like technological cathedrals devoted to catching the aftermath of tiny events. They measure tracks, energies, directions, and particle types. From millions upon millions of collisions, physicists search for patterns that reveal a small excess, a repeated hint that something with the properties of the Higgs boson was briefly present. There is something quietly impressive about this kind of discovery. No one saw a glowing little Higgs boson drift across a screen with a label attached. Instead, thousands of scientists worked together to find a statistical pattern in a mountain of data. They looked for the ways the Higgs boson should decay, compared those possibilities with known background processes, and asked whether the data contained more events than expected in just the right places. It was a discovery made not by a single dramatic snapshot, but by careful accumulation. Nature whispered, and physicists built a machine large enough to hear the whisper. The announcement came in 2012, when 2 independent experiments at the Large Hadron Collider reported the discovery of a new particle with properties matching the Higgs boson. It was a historic moment, not because it completed physics, but because it confirmed a central part of the Standard Model that had remained unobserved for decades. The field that had been introduced to solve deep theoretical problems was not merely an elegant idea. It had a ripple, and the ripple had been found. The Higgs boson is often described as heavy, but in particle physics, heavy means something different from the heaviness of a suitcase. It means the particle has a large mass compared with many other elementary particles. Because it is heavy, producing it requires high energy. This is one reason it took so long to discover. Earlier accelerators did not have enough reach or enough data to reveal it clearly. The Large Hadron Collider was powerful enough to create Higgs bosons and sensitive enough through its experiments to identify their traces. Its heaviness also affects how it decays. A Higgs boson can decay into different combinations of particles. Some of these decay paths are easier to detect than others. One especially clean path involves 2 photons. Photons are particles of light, and detectors can measure them well. Another important path involves particles associated with the weak force. Another involves heavy matter particles, because the Higgs field interacts more strongly with heavier particles. This is a crucial clue. The Higgs boson tends to connect more strongly to particles that have stronger interactions with the Higgs field. In this way, its decay patterns are not random decoration. They're a map of the field relationships that give particles mass. This is why physicists did not stop at finding something that looked vaguely like a Higgs boson. They had to measure its behavior. Does it have the expected spin? Does it decay into the expected particles at the expected rates? Does it interact with weak force particles as predicted? Does it interact with heavy quarks and heavy leptons as predicted? Every measurement tests whether the particle is truly the Standard Model Higgs boson, or whether it is only a close relative, perhaps part of a larger and stranger Higgs sector. So far, the particle found behaves very much like the Standard Model Higgs, within the precision of measurements. That is both satisfying and slightly frustrating, because many physicists hoped it might immediately reveal cracks in the theory. Nature, with excellent comic timing, gave exactly enough mystery to keep everyone employed, but not enough to make the next answer obvious. The fact that the Higgs boson has no electric charge is important. It is not a charged particle like the electron. It is also a scalar particle, meaning it has no spin in the way other known elementary particles do. This made it unique at the time of discovery. Before the Higgs boson, every known fundamental particle had spin. The Higgs boson was the first observed fundamental scalar particle. That may sound like a technical detail, but it changes the character of the field. A scalar field can fill space without pointing in any direction. It can have a value everywhere while leaving ordinary space looking the same in every direction. This is one reason the Higgs field can quietly shape particle masses without making the universe visibly lopsided. The boson also tells us about the stiffness, in a sense, of the Higgs field. When a field is excited, the mass of its particle tells physicists something about how costly it is to make that excitation. A light excitation is easier to produce. A heavy excitation requires more energy. The Higgs boson mass is therefore not just another number in a table. It gives information about the field itself and about the shape of the Higgs field energy landscape. That landscape is not a literal terrain, but the metaphor helps. The Higgs field settled into a vacuum state, and the boson represents a small disturbance around that settled state. By measuring the boson, physicists learn about the local shape of the valley in which the field rests. This leads to one of the more unsettling questions connected with the Higgs: is our vacuum stable? The measured properties of the Higgs boson, together with the mass of the top quark and other parameters, suggest that the universe may be in a state that is long-lived, but not necessarily the deepest possible state. This does not mean anything dramatic is about to happen. If the vacuum is metastable, its lifetime could be far longer than the current age of the universe by an absurd margin. It is not a bedtime emergency. Still, it is a profound idea. The Higgs field may be sitting in a valley that is stable for all practical cosmic purposes, while another deeper valley could exist in principle. Physics has a way of making even empty space sound like it has long-term plans. The Higgs boson is therefore a messenger from the vacuum. It tells us that empty space has structure. It tells us that the field responsible for electroweak symmetry breaking can be excited. It tells us that the masses of elementary particles are tied to something physically testable. It also raises questions about why the Higgs field has the properties it does. Why is the Higgs boson mass not much larger? Why are its interactions arranged as they are? Why does the field settle into the value we observe? These questions point beyond the mere discovery of the boson toward the deeper question of what the Higgs field really is. The discovery also changed the emotional shape of particle physics. For decades, the Higgs boson was the missing piece of the Standard Model. Its absence was like a reserved seat at a dinner table where every other guest had arrived. Physicists could see where it should fit. They could describe why it mattered. But until it was found, there remained a gap between theory and observation. When it finally appeared, the Standard Model became complete in one important sense. All its predicted particles had been observed, but completion is not the same as finality. A house can have all its rooms and still sit on land that nobody fully understands. One reason the Higgs boson does not feel like an ending is that it appears strangely ordinary. It behaves very close to expectation. That may sound reassuring, and it is, but scientists often learn new physics from deviations. A small mismatch can reveal a hidden particle, a new force, or a deeper symmetry. So far, Higgs measurements have not shown a clear departure from the Standard Model. The ripple is there, but it has not yet carried a message from new physics in a language we can clearly read. Future experiments may measure it more precisely. A tiny difference in how often it decays one way rather than another could point toward unknown particles influencing the process. The Higgs boson is not only a discovery already made, it is an instrument still being used. The way the Higgs boson is produced also matters. At the Large Hadron Collider, the most common production process involves gluons inside protons. Gluons do not interact directly with the Higgs field in the same simple way massive matter particles do, but they can produce a Higgs boson through effects involving heavy quarks, especially the top quark. There are also processes where weak force particles combine to produce a Higgs boson, or where a Higgs boson is produced alongside other particles. Each production path tests a different part of the Higgs story. The field is connected not just to one particle, but to the full network of Standard Model interactions. If this sounds complicated, that is because it is. Yet the central image can remain gentle. The Higgs field fills space. A powerful collision can disturb it. That disturbance appears as a Higgs boson. The boson vanishes quickly, but its decay products reveal that it was there. By studying those decay products, physicists learn how the Higgs field interacts with other particles. The ripple teaches us about the sea. There is another common misconception worth smoothing out. The Higgs boson was not discovered by smashing particles together and finding a tiny object hidden inside them. Protons do not contain Higgs bosons in the way a raisin bun contains raisins. The collision energy created a Higgs boson by exciting the Higgs field. This is a key difference. In quantum field theory, particles can be created and destroyed when energy is transformed according to the allowed rules. A Higgs boson is not mined from the interior of matter. It is produced when the field is given enough energy in the right way. This is why particle accelerators are sometimes described as microscopes, but they are also more than microscopes. They do not merely look at smaller things. They create conditions where fields reveal their possible excitations. High-energy collisions allow nature to display particles that are not normally present around us. These particles may have existed abundantly in the early universe, when temperatures were far higher. In that sense, colliders are not only looking inward to small distances, they're also reaching backward toward conditions that once filled the young cosmos. The Higgs boson belongs to both stories. It is a tiny quantum excitation and a clue to the early state of the universe. The early universe was hot enough that the Higgs field behaved differently from how it behaves now. As the universe cooled, the field settled into its present vacuum value. The Higgs boson we observe today is a ripple around that settled value. This means that the particle discovered in colliders is not the whole Higgs story, but a sign of the current state of the field. To understand the field completely, physicists would like to know not only how it interacts with other particles, but how it interacts with itself. The Higgs field should have self-interaction, meaning Higgs bosons can, in principle, reveal how the field shapes its own energy landscape. Measuring that self-interaction is extremely difficult, but it is one of the major goals for future experiments. Self-interaction matters because it tells us more about the phase transition in the early universe and the stability of the vacuum. It may also connect to the question of why matter survived over antimatter. Some theories beyond the Standard Model suggest that the Higgs field transition in the early universe could have played a role in creating the matter-dominated universe we inhabit, but the Standard Model alone does not seem sufficient for that. If future measurements of Higgs self-interaction or rare Higgs decays show unexpected behaviour, they could point to new physics linked to these cosmic puzzles. The Higgs boson might also connect to dark matter. Since the Higgs field interacts with mass-giving mechanisms, and since the Higgs boson can in some theories act as a bridge between known particles and hidden particles, physicists search for signs that Higgs bosons decay into invisible particles. Invisible here means particles that pass through detectors without leaving ordinary tracks, much like neutrinos do, though dark matter candidates would be something else. If a Higgs boson sometimes decayed into dark matter particles, detectors would infer missing energy and momentum. So far, no confirmed signal has appeared, but the search continues because the Higgs field may be one of the few portals between the known Standard Model and whatever dark matter is. There is also the question of whether there is only one Higgs boson. The Standard Model has one Higgs field and one physical Higgs boson after electroweak symmetry breaking. But many theories beyond the Standard Model predict additional Higgs-like particles. There could be heavier scalar particles, charged Higgs particles, or several related fields. Experiments have looked for these possibilities and have not found confirmed evidence yet. Still, the existence of one Higgs boson makes the question natural. If nature has one scalar field, perhaps it has more. The discovered Higgs might be the simplest member of a larger family, or it might be alone. At the moment, measurements lean toward the simple picture, but the door is not closed. The boson therefore sits in a peculiar position. It is a triumph of the Standard Model, but also one of the best places to search for what lies beyond it. It confirmed the mechanism that gives mass to elementary particles, but it did not explain why the Higgs field itself has its particular form. It completed a particle list, but it opened new questions about vacuum stability, dark matter, matter-antimatter imbalance, and deeper naturalness problems. It is both answer and question. That is very typical of physics, which often behaves like a polite hallway. Every door you open reveals 3 more doors, all labelled in smaller handwriting. For anyone listening quietly, the scale of the experimental achievement may be worth lingering on. The Higgs boson is born in a collision far smaller than an atom, lives for a time so brief that ordinary imagination cannot hold it, and vanishes into other particles before it can travel any meaningful distance. Yet humans built instruments large enough, precise enough, and patient enough to identify it. The discovery required not only machinery, but trust in shared methods. It required independent experiments, careful analysis, repeated checks, and the willingness to say not yet until the evidence became strong. It was not a lucky glimpse, it was a carefully earned conclusion, and still, the Higgs field itself remains quietly present everywhere, not only in the collider tunnel. The Higgs boson is rare in ordinary conditions because exciting the field enough to produce one takes enormous energy. But the field does not need to be excited to do its everyday work. Its vacuum value is always there. Electrons do not need a nearby Higgs boson to have mass. Quarks do not wait for Higgs bosons to pass by. The mass-giving mechanism comes from the background field, not from a constant exchange of real Higgs bosons in matter. This is another place where language can mislead. The boson proves the field, but the field does the quiet work. A helpful comparison is a bell. A bell can sit silently in a room, and its shape affects what sounds it can make. Strike it, and you hear a tone. The tone reveals something about the bell. But the bell existed before the tone and after it. The Higgs field is not a bell made of metal, of course, but the relationship is similar. The Higgs boson is the tone produced when the field is struck hard enough. The tone is brief. The field remains. The Large Hadron Collider struck the field through high-energy proton collisions. The detectors listened. The data revealed the tone. Since then, physicists have been studying whether that tone is exactly what the Standard Model predicts, or whether it carries faint harmonics from unknown physics. Each new measurement narrows the possibilities. Sometimes the absence of surprise is itself information. It tells scientists which ideas are less likely, which energy ranges are constrained, which hidden particles cannot interact too strongly with the Higgs field. Science advances not only by finding new things, but by learning where new things are not. The Higgs boson also teaches humility about the word made. In ordinary life, if something ripples, we ask what substance is rippling. Water ripples, fabric ripples, air can carry pressure waves. With the Higgs field, the field is not made of ordinary substance. It is a fundamental field in our current theory. The boson is not made of smaller known pieces within the Standard Model. It is the quantum of the Higgs field. Asking what the Higgs boson is made of leads back to the field, and asking what the field is made of leads to the deeper uncertainty we're moving toward. It may be fundamental, it may be composite, it may be connected to hidden layers we have not yet reached. The boson is our experimental handle on that question. So the Higgs boson is not merely famous because it was difficult to find. It is famous because it lets the invisible field become testable. It turns the mass-giving mechanism from a hidden feature of equations into a physical phenomenon with measurable consequences. It shows that the vacuum has a field capable of excitation. It confirms that the Standard Model was pointing towards something real, and it gives physicists a delicate instrument for probing the next layer of reality. The story now sits in a careful place. We have seen the field as the background, the boson as the ripple, and the collider as the instrument that made the ripple visible through evidence. But the original question remains patiently waiting. If the Higgs field fills empty space, if it gives mass to elementary particles, if its boson has been found, then what is the field itself? Is it truly fundamental, one of the basic ingredients of nature, or is it a surface effect of something deeper? Is it smooth all the way down, or does it hide an inner structure the way protons once hid quarks? To ask what the Higgs field might really be made of, we need to step beyond what has been confirmed and carefully separate established physics from the tempting possibilities that still hover at the edge of the map. The first careful answer is less dramatic than the question might invite. In the Standard Model, the Higgs field is not made of anything smaller that we know about. It is treated as fundamental. That means it is not built from electrons, quarks, gluons, photons, or any other known particles. It is not a mist of tiny Higgs grains drifting through space. It is not a hidden fluid with little droplets. It is not an invisible dust spread between the stars. It is a field, and in our present best-tested theory, that field is one of the basic ingredients of nature. That answer can feel a little unsatisfying, like asking what a wall is made of and being told, very calmly, woolness. But in physics, calling something fundamental is not meant to be evasive. It means that, as far as experiments have shown, the thing does not reveal an inner structure. The electron is also treated as fundamental in the Standard Model. We do not know it to be made of smaller parts. A quark is treated as fundamental too. The photon is an excitation of the electromagnetic field, not a little machine assembled from tinier pieces. The Higgs field belongs to that same kind of description. It is part of the starting furniture of the theory, not something assembled later from known materials. But the question remains worth asking, because physics has been wrong before about what was truly fundamental. Atoms were once named as though they could not be cut into smaller things. Then they turned out to contain electrons and nuclei. Nuclei turned out to contain protons and neutrons. Protons and neutrons turned out to contain quarks and gluons. Each time, nature allowed us to think we had reached the bottom, then quietly opened a lower door. So when physicists say the Higgs field is fundamental, they do not mean curiosity must stop. They mean that no confirmed experiment has yet shown a deeper layer beneath it. The difficulty begins with the word made. In ordinary life, made of means material parts. A wooden chair is made of wood. A brick wall is made of bricks. A cake is made of flour, eggs, sugar, and the optimistic belief that you remembered to preheat the oven. If we ask what something is made of, we expect smaller pieces. But quantum fields are not ordinary objects. A field is not a pile of parts in space. A field is something that exists at every point in space and time, with rules for how it can change, interact, and be excited. The Higgs boson is an excitation of the Higgs field, but the Higgs field itself is not made from Higgs bosons in the everyday sense. The boson is what appears when the field ripples. The field is the underlying thing. This is a little like asking what the ocean is made of and answering waves. That answer is backward. Waves are made from the ocean moving. The ocean is not made from waves. In the same way, the Higgs boson is a ripple in the Higgs field. The field is not a collection of bosons sitting quietly until needed. In ordinary empty space, there are no real Higgs bosons floating around, yet the Higgs field is still present through its background value. That background value is the part that gives masses to elementary particles. The Higgs boson is the brief disturbance that allowed scientists to confirm the field exists. So if the Higgs field is not made of known particles, what is it made of in the Standard Model? The most honest answer is that it is made of itself. In the same way, the electromagnetic field is not made of photons, but can produce photons when excited. This sounds strange only because our minds keep reaching for little solid objects. Fields are more basic than that picture. They are not substances in space. They are part of what space contains at the deepest level of our current theory. The Higgs field is also unusual because it is a scalar field. That means it has a value without pointing in a direction. A magnetic field points. An electric field points. If you place a tiny compass in a magnetic field, it turns because the field has directional character. The Higgs field does not work like that. It does not point north, east, upward, or toward the biscuits. It simply has a value. That makes it able to fill empty space without choosing a visible direction. Space can still look the same in every direction, while the Higgs field remains present everywhere. That scalar nature is one reason the Higgs field feels so mysterious. It was the first fundamental scalar field confirmed in experiment. Before the Higgs boson was discovered, scalar fields were common in theories, but not directly established as basic ingredients of nature. The Higgs changed that. It showed that at least one such field is not merely a mathematical convenience. It has a real excitation. It can be disturbed. It can produce a measurable particle. This makes physicists wonder whether other scalar fields may exist too. Some ideas about the early universe involve them. Some ideas about dark energy involve them. But those are separate questions, and the Higgs field itself should not be forced to solve every mystery just because it is already unusual. In the Standard Model, the Higgs field has an internal structure, but not a structure made of little pieces like beads on a string. It is described as having several internal components before symmetry breaking, and after the field settles into its vacuum state, most of those components become tied to the massive weak force particles, while one remains as the physical Higgs boson. That is a technical way of saying the field has more richness than a single ordinary number, but it still does not mean it is made of smaller particles. Its internal mathematical structure belongs to how it transforms under the electroweak symmetries of the theory. That structure is why it can do the job it does. The Higgs field is also tied to the shape of the vacuum. In ordinary thinking, the vacuum is empty space. In quantum field theory, the vacuum is the lowest energy state of the fields. The Higgs field has a non-zero value in that state. The field does not rest at nothing. It rests at something. This is the strange feature that allows particles to interact with it everywhere. The electron does not need to find a lump of Higgs field. The Higgs field is already present in the vacuum, and the electron field is defined within that background. If that is the established picture, then the speculative possibilities begin with a simple thought. Perhaps the Higgs field only looks fundamental because we have not yet looked closely enough. Perhaps, at smaller distances or higher energies, it will reveal that it is made of deeper ingredients. This kind of idea is called a composite Higgs idea. Composite means made of parts. In such theories, the Higgs boson would not be truly elementary. It would be more like a proton or a pion, a particle that behaves as one object at low energies, but is secretly built from more basic constituents bound together by a new force. This is not a confirmed idea. It is a possibility. It is attractive to some physicists because it could help explain why the Higgs boson has the mass it has. In the standard model, the Higgs mass appears sensitive to effects from very high energy scales. That sensitivity makes many physicists uneasy. It looks as though the Higgs should naturally become much heavier, unless something protects it or balances contributions from unknown physics. A composite Higgs could be protected by its underlying structure in a way that makes its observed mass less puzzling. Again, this is not a proven answer. It is a proposed deeper mechanism. A useful comparison is the proton. If you study a proton gently, it behaves like a single particle with a definite mass, charge, and spin. But when high-energy experiments probe it deeply, its inner structure becomes visible. Quarks and gluons appear in the data. The proton is not fundamental. It is a bound state. A composite Higgs theory asks whether the Higgs might be similar in spirit, though not made of ordinary quarks and gluons. It would be made of new, unknown ingredients held together by a new, unknown interaction. At low energies, it would look like a simple scalar particle. At higher energies, if we could reach them, it might reveal the deeper machinery inside. So far, experiments have not shown that the Higgs is composite. The Higgs boson behaves very much like the standard model predicts. Its measured interactions are close to expectation. If it has substructure, that substructure is hidden well enough that present experiments have not exposed it. This does not rule out all composite possibilities, but it pushes them into more constrained territory. The Higgs, if composite, must be subtle. Another family of ideas involves supersymmetry. Supersymmetry is a proposed relationship between matter particles and force particles. It suggests that every known particle has a partner particle with different spin. One reason physicists studied supersymmetry so intensely is that it could protect the Higgs mass from becoming unnaturally large. The contributions from known particles and their supersymmetric partners could balance in a way that stabilizes the Higgs. In many supersymmetric theories, there is not just one Higgs field. There are multiple Higgs fields, leading to several Higgs-like particles. The Higgs boson we found would then be only one member of a larger family. This is a beautiful idea mathematically, but nature has not yet confirmed it. Experiments have searched for supersymmetric particles, and no clear discovery has appeared. That does not prove supersymmetry is false in every form, because the partner particles could be heavier or more elusive than early hopes suggested. But it does mean the simplest and most obvious versions have been squeezed. For our question, supersymmetry offers one possible answer to why the Higgs field has its properties, but it does not yet tell us what the Higgs field is made of in confirmed reality. It remains a possibility waiting for evidence. Then there are ideas involving extra dimensions. These do not mean extra dimensions in the casual science fiction sense of a glowing portal behind the wardrobe, though that would certainly make moving house more interesting. In some theories, space may have additional dimensions beyond the three we move through, curled up or hidden in ways too small to notice directly. The Higgs field might be connected to the geometry of those extra dimensions. Its properties could arise from how fields behave in a higher dimensional space. From our perspective, the Higgs would look like a field filling ordinary space. From the deeper perspective, it might be part of a larger geometric structure. Again, this is speculative. Extra-dimensional theories can be elegant and useful in theoretical work, but no experiment has confirmed that such dimensions exist. The Higgs field may be a clue, or it may not. Physics has many elegant staircases that do not yet lead to a discovered room. Another possibility is that the Higgs field is connected to a hidden sector. A hidden sector means a set of particles and fields that interact very weakly with the particles we know. Dark matter may belong to such a sector. If there are hidden particles, the Higgs field might be one of the few ways they can communicate with ordinary matter. This is sometimes described as a portal idea. The Higgs field could act like a quiet doorway between the standard model and something beyond it. If that were true, Higgs bosons might sometimes decay into invisible particles, or Higgs properties might show tiny deviations from standard model predictions. Experiments search for this. They look for Higgs decays that seem to produce missing energy, which could hint at invisible particles leaving the detector unseen. They also measure Higgs interactions with known particles as precisely as possible, because hidden particles could subtly affect those interactions. So far, there is no confirmed sign of a hidden sector through the Higgs, but the search is important because the Higgs field has the right kind of position in the theory to connect known mass with unknown mass. There is also a more radical possibility. The Higgs field may be emergent. Emergent means that something appears at one level of description, but is not fundamental at a deeper level. Temperature is emergent. A single molecule does not have temperature in the everyday sense. Temperature arises from the collective motion of many molecules. Sound is emergent. It is a pressure wave moving through matter, not a separate substance. Perhaps the Higgs field is similar. Perhaps it emerges from deeper quantum ingredients we have not identified. At our energies, it looks like a fundamental field. At a deeper level, it might be a collective behaviour. This idea is attractive because emergence is common in physics. Many things that seem basic at one scale become collective at another. A crystal has vibrations that behave like particles, even though they arise from atoms arranged in a lattice. Superconductors have collective fields that give photons an effective mass inside the material, a phenomenon that helped inspire thinking related to the Higgs mechanism. These examples do not prove the Higgs field is emergent, but they show that nature can produce field-like behavior from deeper structure. A future theory might describe the Higgs not as a starting ingredient, but as the low-energy appearance of something more basic. If that is true, the Higgs field would be less like a stone and more like a pattern. Not a material object, but a stable behaviour arising from deeper rules. This would not make it unreal. Temperature is real. Sound is real. Waves are real. Emergent things can shape the world powerfully. The question is not whether the Higgs field exists. The evidence for the field is strong. The question is whether it is fundamental or emergent. There are also theories in which the Higgs is related to a pseudo-Nambu-Goldstone boson. That phrase is a mouthful, and not a very sleepy one, so we can treat it gently. The basic idea is that certain particles can arise when a symmetry is broken. If the symmetry is exact, the resulting particle can be massless. If the symmetry is only approximate, the particle can be light but not massless. Some composite Higgs theories use this idea to explain why the Higgs boson is lighter than the deeper energy scale might suggest. The Higgs would then be protected by symmetry, like a delicate object kept safe inside a well-designed case. This kind of model tries to combine compositeness with symmetry protection. No confirmed evidence has shown that this is the case. but it demonstrates the kind of thinking physicists use. The Higgs looks puzzling because it is light compared with some expectations. Symmetry may protect it, compositeness may explain it, new particles may stabilize it, hidden dimensions may reshape it. Or perhaps our expectations about what counts as natural are not reliable guides. Nature may simply have chosen values that look surprising to us because our theoretical instincts are incomplete. That last possibility is important. It is tempting to assume that every puzzling number must have a neat mechanism behind it. Sometimes that is true. The periodic table once looked like a list of chemical facts until atomic structure explained it. The spectrum of light from atoms once looked like a pattern of mysterious lines, until quantum mechanics explained it. But sometimes a parameter may be part of the environmental facts of a particular universe. Some physicists connect this thought to multiverse ideas, where different regions or universes have different values for fields and constants, and we observe a region compatible with complex matter because otherwise we would not be here. This is controversial, and not everyone finds it satisfying. It may be true, false, or incomplete. But the Higgs field often appears in these discussions because its value affects whether atoms and stable matter can exist. The measured Higgs mass also relates to vacuum stability. The current data suggest that our vacuum may be stable, or perhaps metastable, depending on precise values of other particle properties, especially the top quark. Metastable means long-lived, but not necessarily the deepest possible state. This does not mean anything dangerous is expected. If the vacuum is metastable, its lifetime could be vastly longer than the age of the universe. But the idea is astonishing. The Higgs field may determine whether empty space is sitting in a final resting state, or in a state that is stable for all practical purposes, but not absolutely final. Empty space, once again, is not so empty. This question of stability also connects to the shape of the Higgs field energy landscape. The field rests in its current vacuum state because that state is energetically favoured under present conditions. But the full shape of that landscape depends on Higgs self-interaction and on the influence of other particles. Physicists would like to measure how the Higgs field interacts with itself more precisely. Producing two Higgs bosons at once is one way to probe that self-interaction, but it is extremely rare and difficult. Future data may reveal whether the Higgs self-interaction matches the standard model or hints at something deeper. If it differs, it could be one of the first cracks in the simple picture. The Higgs field might also have played a role in the early universe beyond giving particles mass. When the universe cooled and the Higgs field settled into its present state, the nature of that transition may have mattered. In the standard model, the transition does not seem strong enough to explain why matter came to dominate over antimatter. But in theories with additional Higgs fields or new particles, the Higgs transition could be more dramatic and could help create the conditions for matter to survive. This would connect the Higgs field not only to mass, but to the very fact that there is matter around us at all. Again, this is not established, but it is one reason the Higgs remains central to future particle physics. The difficulty with all these ideas is that they need evidence. A theory can be elegant, clever, and deeply satisfying, but physics asks for contact with the world. Does it predict new particles? Does it shift Higgs couplings? Does it change rare decays? Does it produce signals in collider data? Does it connect to dark matter searches or cosmological observations? The Higgs field might be fundamental, composite, emergent, protected by symmetry, linked to hidden sectors, or part of a larger scalar family. At the moment, the simplest confirmed picture is still the standard model one. The Higgs field behaves as though it is fundamental within the range we have tested. That answer may seem modest, but it is not small. A fundamental scalar field filling the universe is already astonishing. It means that empty space has a built-in condition that gives masses to elementary particles. It means the vacuum is active in defining the particle world. It means a field with no direction and no ordinary substance shapes the electron, quarks, and the weak force. Even if the Higgs field is truly fundamental and no deeper layer exists, it remains one of the strangest features ever discovered. But if it is not fundamental, then the Higgs field may be the first visible edge of a hidden continent. Its boson may be like the first ripple from a sea whose depth we have not measured. The field may be telling us that the standard model is a low-energy surface, a calm visible layer above more intricate physics. To find out, physicists need more precise measurements. They need to study how the Higgs boson decays, how it is produced, how it couples to lighter particles, whether it interacts with itself as expected, and whether it ever disappears into invisible states. The Higgs is no longer only a missing particle, it is a tool for listening to what may lie beyond the known theory. So what might the Higgs field really be made of? It might be made of nothing smaller at all. It might be fundamental, a basic field of the universe. It might be composite, built from unknown constituents bound by a hidden force. It might be emergent, a collective pattern arising from deeper quantum structure. It might be one member of a larger family of fields. It might be connected to dark matter, extra dimensions, supersymmetry, or early universe transitions. The honest answer is that we do not yet know which of these, if any, nature has chosen beyond the standard model. The confirmed fact is that the Higgs field exists as a field with measurable consequences, and the Higgs boson is its ripple. The deeper composition, if there is one, remains hidden. There is a calm kind of beauty in that uncertainty. The Higgs field was once itself an invisible proposal, a solution written into theory long before experiment found its ripple. Now it is part of established physics, yet it has become a doorway to new questions. It shows how science advances. A mystery becomes a mechanism. The mechanism becomes a discovery. The discovery becomes a sharper mystery. Each answer gives the next question a clearer shape. For the matter around you, the deeper answer is not needed for the field to do its work. Whether the Higgs field is fundamental or emergent, simple or composite, alone or part of a hidden family, its present value still helps electrons and quarks have the masses they have. It still helps the weak force behave as it does. It still helps the universe support atoms, stars, chemistry, planets, and living bodies. The unknown depth beneath the field does not make its visible consequences uncertain. It only reminds us that familiar matter may rest on an even deeper foundation than we can currently see. And that brings the question gently back from speculation to the room around you. The Higgs field is not just an exotic idea for particle accelerators. Its influence is written into the structure of ordinary matter. It helps decide how electrons behave in atoms, how quarks contribute to the particles inside nuclei, and how the weak force participates in the life of stars. To understand why this field matters beyond theory, we need to follow its consequences outward, from the hidden vacuum into atoms, from atoms into starlight, and from starlight into the slow, delicate chemistry that makes a world like ours possible. To see why the Higgs field matters for stars, atoms, and us, it helps to bring the whole idea down from the high ceilings of particle physics and place it gently on the table beside familiar things: a glass of water, a warm lamp, a sleeping hand resting on a blanket. The Higgs field sounds distant because it belongs to the language of colliders, symmetry, quantum fields, and the early universe. But its influence is not locked away in underground machines. It is present in the basic properties of the particles that make ordinary matter possible. It is part of the reason atoms have the sizes they have, why the weak nuclear force behaves as it does, why stars burn in their particular slow and steady way, and why the universe contains stable structures instead of only a bright rush of weightless motion. The simplest place to begin is the atom. An atom is not a tiny solid bead. It is a small system made from a nucleus surrounded by electrons. The nucleus contains protons and neutrons, and those protons and neutrons contain quarks bound together by the strong nuclear force. The electrons are much lighter than the nucleus, yet they are essential because their arrangement determines chemistry. The way electrons occupy regions around nuclei gives atoms their personalities. Hydrogen is not oxygen. Carbon is not gold. Sodium and chlorine each have their own behaviour, and when they meet in the right way, they can become table salt, which is a rather dramatic transformation for two elements that separately are not exactly ideal dinner companions. The Higgs field matters here because electrons have mass through their interaction with it. That mass is small compared with the mass of protons and neutrons, but it is not optional. The electron mass helps set the scale of atoms. It affects how tightly electrons can be bound to nuclei, how large atoms are, how much energy is involved when electrons shift between different states, and how chemical bonds form. If the electron mass were very different, atoms would not merely be a little heavier or lighter, their structure would change, chemistry would change, the sizes of molecules would change, the energy needed to rearrange electrons would change. The familiar world of water, rocks, air, proteins, sugars, metals, pigments, and living cells would be rewritten from the inside. It is tempting to say that atoms are mostly empty space, and in one sense that is true. The nucleus is tiny compared with the spread of the electron cloud, but that empty-looking space is not meaningless. It is shaped by quantum rules, electromagnetic attraction, and the mass of the electron. The electron is not orbiting like a tiny moon around a tiny planet. It occupies quantum states. Its mass plays a role in the size and energy of those states. Without the Higgs field giving the electron a rest mass, the electron would not behave like the electron we know. The atom would lose one of the basic ingredients that makes it stable in its familiar form. This does not mean the Higgs field alone builds atoms. Electromagnetism holds electrons to nuclei. Quantum mechanics determines the allowed electron states. The strong nuclear force holds the nucleus together. The Higgs field is part of the foundation rather than the whole building. It gives certain elementary particles their masses, and those masses enter the larger structures that other forces organise. If physics were a quiet kitchen, the Higgs field would not be the entire recipe, but it would be one of those ingredients whose absence changes everything, even if it is not the flavour you notice first. The nucleus brings in a second layer. Protons and neutrons get most of their mass not directly from the Higgs field, but from the energy of the strong nuclear force inside them. Quarks and gluons are confined in a restless, energetic system, and that energy accounts for most of the proton and neutron mass. This fact is important because it keeps us honest. The Higgs field is not the source of all mass in ordinary matter. Most of the mass in your body comes from the strong force energy inside protons and neutrons. Still, the Higgs field remains crucial because quarks do get their own masses through it, and those quark masses influence the behaviour of protons, neutrons, and nuclear forces. A proton and a neutron are similar, but not identical. Their small mass difference matters greatly. It helps determine which particles are stable, which can decay, and how nuclear reactions proceed. If the masses of quarks were different, the balance between protons and neutrons could change. Hydrogen might not be stable in the same way. Atomic nuclei might form differently, or not form many familiar elements at all. The universe depends on many balances that seem small when written in a particle physics table, but become enormous when carried outward into cosmic history. Change the quark masses too much, and the periodic table may not survive in anything like its known form. The strong force between protons and neutrons inside nuclei is also affected indirectly by quark masses. The nuclear force is not simply the strong force in its raw form. It is a leftover interaction between composite particles shaped by the behaviour of quarks and gluons. The masses of certain short-lived particles involved in this nuclear binding depend on quark masses, and quark masses depend on the Higgs field. This means the Higgs field helps influence the range and strength of the nuclear forces that allow atomic nuclei to exist. It does not do this alone, and it does not act like glue between protons and neutrons, but its fingerprints are present in the values that make nuclear matter possible. Now move from atoms to stars. Stars are sometimes described as giant balls of burning gas, but that phrase is both useful and misleading. They are not burning like wood in a fireplace. They shine because of nuclear fusion. In the cores of stars, light atomic nuclei are pressed together under enormous temperature and pressure. When conditions are right, they combine into heavier nuclei, releasing energy. That energy works its way outward and eventually becomes the light and warmth that planets receive. The sunlight that reaches Earth began as nuclear processes deep in the sun, then spent a long time wandering through solar material before finally escaping into space. It arrives on your face as warmth, on leaves as fuel for photosynthesis, and on a sleepy room as the reason morning eventually happens whether or not anyone feels ready for it. The Higgs field matters for stars in several ways. First, stars depend on the masses of particles. The electron mass affects atoms and plasma behavior. Quark masses affect protons, neutrons, and nuclei. The masses of weak force carriers affect the weak nuclear interactions that play key roles in stellar fusion. In the Sun, the main fusion process begins with protons, but two protons do not simply become a stable helium nucleus by sticking together at once. One of the protons must be transformed into a neutron through the weak interaction. This step is slow, very slow, and that slowness is a blessing. If the weak interaction were much stronger or behaved over a longer range, stars like the Sun might burn through their fuel far more quickly. If it were much weaker, fusion might struggle to proceed in the way needed for stable starlight. The weak force has its short range partly because its carriers are massive, and their mass comes from the Higgs field. So the Higgs field is connected to the pace at which stars like the Sun release energy. Not by acting as fuel, and not by shining itself, but by helping set the properties of the weak force. The Sun has been shining for billions of years in part because the weak step in its fusion chain is rare enough to make the process slow and steady. That steadiness gives planets time for surfaces to cool, oceans to form, chemistry to become complex, and life to begin its long uncertain work. This is a striking thought. The same Higgs field that gives mass to particles in the Standard Model is linked, through the weak interaction, to the slow-burning lifetime of stars. A universe with a different Higgs field value could have different weak force carrier masses, different electron and quark masses, and different nuclear reaction rates. Stars might flare violently and die quickly, or fail to ignite in familiar ways, or produce different elements. The night sky would not simply be rearranged. The entire history of matter could change. The weak force also matters in the lives and deaths of stars. In massive stars, nuclear processes build heavier elements through successive stages. When such stars reach the end of their lives, some collapse and explode as supernovae. Neutrinos, which interact through the weak force, play an important role in these events. They carry away vast amounts of energy and influence the dynamics of stellar collapse and explosion. The weak interaction is subtle in everyday life because it is short-ranged, and not something our senses notice directly. Yet in the heart of a dying star, it becomes part of one of the universe's most powerful transformations. Supernovae help seed space with elements made in stars and in explosive environments. The calcium in bones, the iron in blood, the oxygen in water, the carbon in living tissue, all belong to a cosmic story of nuclear processes. The Higgs field is not the sole author of that story, but it helps set some of the particle properties that allow the story to unfold. It contributes to the masses and interactions that shape nuclear stability, fusion pathways, radioactive decay, and stellar evolution. Without the Higgs field as we know it, the elements needed for rocky planets and living chemistry might not be produced or preserved in the same way. The Higgs field also matters because it helps distinguish matter from radiation in a practical sense. Massless particles like photons always move at the speed of light in empty space. They cannot be at rest. Massive particles can move slowly. They can gather. They can form atoms. They can be part of solid, liquid, and gaseous matter. The universe needs both radiation and matter, but they behave very differently. Radiation streams. Matter can clump. Radiation can carry energy across space. Matter can build planets, oceans, minerals, and bodies. The Higgs field helps make many elementary particles massive, giving them the possibility of moving slower than light and becoming part of structures. Gravity then takes over on large scales. Gravity gathers matter into clouds, stars, galaxies, and planets. But gravity needs something that can gather. A universe made only of massless particles would not form ordinary atoms and planets in the same way. The Higgs field helps make matter matter-like. That is not a technical phrase, but it captures the point. It helps give particles the properties needed for the slow assembly of complexity. On smaller scales, chemistry depends on electrons, and electrons depend on the Higgs field for their mass. Carbon chemistry is especially important for life as we know it, because carbon can form stable, flexible bonds with many elements, including itself. Those bonds arise from electron behavior. Proteins, DNA, sugars, fats, pigments, and many other biological molecules all depend on the rules of chemistry. Change the electron mass enough, and the balance of chemical bond strengths and molecular shapes changes. Life is not simply sprinkled on top of physics. It is physics organized into chemistry, chemistry organized into biology, and biology organized into the long, imperfect habits of living things. The Higgs field sits deep beneath that chain. The water in a cell also depends on this chain. Water molecules have their shape and polarity because of electron arrangements and the properties of hydrogen and oxygen nuclei. The way water dissolves salts, folds proteins, transports heat, and forms droplets depends on electromagnetic interactions and quantum chemistry. But those interactions play out with particles whose masses are part of the Higgs story. Again, the Higgs field is not making water wet by itself. Wetness is an emergent property of many molecules interacting. But the particles inside those molecules have the properties they do partly because the Higgs field is there. There is a useful caution here. Because the Higgs field is so fundamental, it can be tempting to give it credit for everything. That is not how good physics works. The Higgs field is not responsible for every detail of matter. It does not explain why snowflakes have 6-sided patterns. It does not explain why a particular protein folds one way rather than another. It does not explain consciousness, memory, or why keys disappear exactly when you are late. Those are higher-level phenomena with their own explanations. The Higgs field belongs to the foundation, not every floor of the building. It helps set particle masses. From there, other forces and principles create higher levels of structure. That layered view is important. A living body is not just particle physics, it is also chemistry, thermodynamics, evolution, physiology, and experience. But without the lower layers, the upper layers would have nothing to stand on. The Higgs field is one of those lower layers. It is not the whole story of you, but it is part of the reason the particles in you have the kind of existence that allows atoms, molecules, cells, tissues, and thoughts to appear. The field also matters, because it separates the weak and electromagnetic forces in the universe we know. At high energies, these forces are unified in the electroweak theory. As the universe cooled, the Higgs field settled into its present vacuum value, and the forces became distinct in their low-energy behavior. The photon remained massless, allowing electromagnetism to reach across large distances. The weak force carriers became massive, making the weak force short-ranged. This difference is essential. Electromagnetism shapes atoms and chemistry over atomic distances. The weak force quietly governs certain nuclear changes without overwhelming ordinary matter. The Higgs field helps make that division possible. Imagine if electromagnetism were short-ranged like the weak force. Atoms and chemistry would be unrecognizable. Imagine if the weak force were long-range like electromagnetism. Matter could behave in ways far from what we know. The universe works as it does because the forces have different characters, and the Higgs field helps create one of the most important differences. It leaves the photon massless while giving mass to the weak force carriers. That one distinction echoes outward into stars, atoms, radioactive processes, and the stability of matter. Radioactive decay is another place where the Higgs field matters indirectly. Certain unstable nuclei decay through the weak interaction. These decays affect the composition of matter, the heat inside planets, the dating of ancient rocks, and the processes involved in stellar explosions and element formation. The weak force is not a side note. It is one of the tools by which the universe changes one kind of particle arrangement into another. Since the Higgs field helps set the weak force's short range, it helps determine how those changes occur. The Earth itself is shaped by these processes. Its internal heat comes partly from radioactive decay of elements inside the planet, along with leftover heat from formation. That heat drives geological activity, including mantle convection, volcanic processes, and the movement of tectonic plates. Plate tectonics has influenced climate regulation and the long-term habitability of Earth. This is many steps away from the Higgs field, and we should not pretend the connection is simple. But the chain is real in the broad sense. Particle masses and weak interactions help shape nuclear decay. Nuclear decay contributes to planetary heat. Planetary heat helps shape geology. Geology helps shape environments. Environments shape life. The universe is layered, and deep layers can matter without directly controlling every surface detail. The Higgs field also matters in the early universe. Soon after the Big Bang, the cosmos was hot and dense. Particles and fields existed in conditions very different from those today. As the universe expanded and cooled, the Higgs field settled into its non-zero vacuum value. That transition helped give elementary particles their masses and helped separate the electromagnetic and weak interactions into their familiar forms. Before that transition, the universe was not populated by atoms or stars. It was a hot field-filled environment where particles behaved differently. The later universe of nuclei, atoms, galaxies, stars and planets, depended on the cooling history and on the field states that emerged. This means every atom today carries a connection to early cosmic history. The electron's mass is not just a local fact. It reflects the state of the Higgs field throughout the vacuum. The weak force's short range is not just a laboratory measurement. It reflects the way electroweak symmetry is hidden in the cooled universe. The matter around you is not only made in space, it is shaped by time, by the history of fields settling after the earliest moments. A spoon on a table is old in more than one way. Its atoms were forged in stars and cosmic processes, and the rules that allow those atoms were set by the early behaviour of fundamental fields. The Higgs field's importance also appears in what would happen if its value were different. Physicists sometimes study hypothetical universes with altered constants and particle masses. These are not places we can visit. They are thought experiments and theoretical models. They help us understand how sensitive structure is to fundamental parameters. If the Higgs field value changed, particle masses would generally change. If electron mass changed too much, atoms would change. If quark masses changed, nuclear stability might change. If weak force carrier masses changed, stellar fusion and radioactive processes might change. The known universe seems to occupy a range where complex matter can exist. Whether that fact has a deeper explanation remains unknown, but the Higgs field is central to the question. There is no need to turn this into a mystical claim. The Higgs field does not know we are here. It did not arrange itself for human comfort. But the properties of the Higgs field are among the conditions that allow our kind of matter to exist. Recognizing that can create a quiet sense of perspective. The familiar world is not inevitable from any possible set of rules. It depends on specific relationships among fields and particles. The Higgs field is one of those relationships made physical. For stars, it helps set the weak interaction that controls important fusion steps and stellar processes. For atoms, it helps give electrons and quarks their masses, affecting atomic structure and nuclear behaviour. For us, it lies beneath chemistry, biology, and the matter of our bodies, not as a direct explanation for life, but as part of the foundation on which life's chemistry is built. It is hidden, but not remote. It is quiet, but not irrelevant. Think of a candle flame or a bedside lamp. The light reaching your eyes is electromagnetic radiation, carried by photons that remain massless because of the way the Higgs mechanism leaves electromagnetism unbroken. The atoms in the lamp, the air, the walls, and your eyes contain electrons whose masses come from their interaction with the Higgs field. The nuclei in those atoms contain protons and neutrons whose masses mostly come from strong force energy, but whose detailed behaviour is influenced by quark masses connected to the Higgs. If the electricity powering the lamp came from solar energy, nuclear power, fossil fuels, wind, or water cycles, there are further links to stellar fusion, radioactive processes, planetary geology, and atmospheric physics. A simple light in a room is a meeting point for many layers of nature. This does not mean you need particle physics to enjoy lamplight. It means that ordinary things are deeper than they appear. The Higgs field helps explain why the ingredients of matter have the properties needed for the rest of physics to build with them. It is not a visible support beam. It is more like a rule in the foundation. You do not see it when you enter the house, but the house would not stand the same way without it. There is also a human side to this. The discovery of the Higgs boson showed that people can infer an invisible field from consistency, prediction, and evidence. The field was proposed because a theory needed a way to give particles mass while preserving symmetry. Decades later, a ripple of that field was found. That is a remarkable chain of thought and experiment. It means the quiet matter around us can be connected to ideas tested in machines larger than buildings, and in mathematics precise enough to predict particles before they appear in data. The Higgs field matters not only because it helps make matter possible, but because understanding it shows what science can do. It can reveal that emptiness has structure. It can show that mass is not a simple given. It can connect the light of stars to the hidden state of the vacuum. And still, even after all of this, the Higgs field leaves a deeper mystery. We know it matters. We know its boson exists. We know it fits the Standard Model with impressive success. We know it helps shape particles, atoms, stars, and us. But we do not yet know why the Higgs field has exactly the properties it has. We do not know whether it is truly fundamental or part of a deeper mechanism. We do not know whether it connects to dark matter, the matter-antimatter imbalance, or the earliest moments of cosmic history in ways still hidden from us. Its influence is established, but its deepest origin remains uncertain. That uncertainty does not weaken the story. It gives it direction. The Higgs field is not simply an answer filed away in a completed theory. It is a working part of nature that also points beyond what we currently understand. The same field that helps make atoms possible may also be a clue to unfinished physics. To follow that clue, we have to look beneath mass itself and ask why the universe chose these particle properties, this vacuum state, this balance of forces, and this stable arrangement of matter. The everyday world rests on those choices, and the next step is to sit with the deeper mystery still hiding beneath mass. The deepest mystery beneath mass begins with a strange kind of success. The Higgs field works. It solves a problem that once stood directly in the path of particle physics. It lets the particles of the weak force be massive while leaving the photon massless. It gives electrons and quarks their masses through their interactions with the field. It fits into the Standard Model, and when physicists searched for the Higgs boson, the ripple of that field, they found it. Not vaguely, not as a rumour, but as a measurable particle whose behaviour has so far matched expectations with impressive precision. By any ordinary standard, that is a triumph. And yet, physics is rarely satisfied by a working answer alone. A good answer often behaves like a lamp. It lights the room, but it also reveals the door at the far side of it. The Higgs field explains how many fundamental particles get mass, but it does not fully explain why the pattern of masses is what it is. It tells us that the electron interacts weakly with the Higgs field, while the top quark interacts very strongly. But it does not tell us, in a deep and necessary way, why those strengths have the values they have. It tells us that the Higgs field has a certain background value throughout space. but it does not yet tell us why that value and not another. It tells us that the Higgs boson has the mass we measure, but it does not remove the sense that this mass is oddly delicate. This is the place where the mystery becomes quieter and more serious. The Higgs field is not mysterious because it is vague. It is mysterious because it is precise. It has been measured. It has been tested. It behaves in a definite way. And still, behind that definite behaviour, there are questions the standard model leaves unanswered. The first of these questions is the pattern of particle masses. In everyday life, mass seems like a simple property. A stone has more mass than a feather. A table has more mass than a cup. A person has more mass than a book, unless the book is a very large encyclopedia, and the person is a toddler with strong opinions about bedtime. But in particle physics, mass is not simply a matter of size. The electron is light. The muon, which is like a heavier cousin of the electron, is much heavier. The tau particle is heavier still. Quarks range from very light to extremely heavy. Neutrinos have tiny masses, so tiny that their existence already tells us the simplest standard model picture was incomplete. The Higgs field can assign mass through interaction strength, but the interaction strengths themselves look like a list nature handed us without explanation. Why should the electron be so light? Why should the top quark be so heavy? Why should there be 3 generations of matter particles, each resembling the others but with different masses? Why do the masses span such an enormous range? The standard model accepts these values as inputs. It uses them with great success, but it does not derive them from a deeper principle. That is a very particular kind of ignorance. It is not that physicists cannot measure the masses. They can. It is that the measurements do not yet feel explained. Imagine finding a musical instrument that plays perfectly, but the tuning of its strings seems arbitrary. You can describe every note. You can predict the melody once you know the tuning, but you still wonder why the strings were tightened exactly that way. The Higgs field is tied to the tuning of the particle world, and we do not yet know the reason for the full pattern. Then there is the question of the Higgs field value itself. The field fills the vacuum with a non-zero value. This is what allows particles to acquire mass throughout empty space. But why does the field settle into that value? Why does empty space have this particular condition? If the value were much different, elementary particle masses would generally be different as well. Atoms could change, nuclear processes could change, stars could burn differently. The familiar world might not exist. The field value is therefore not a small detail. It is one of the quiet settings of the universe. One can say that the field has the value it has because of the shape of its energy landscape. That is true within the model, but it pushes the question back one step. Why that landscape? Why that shape? Why those parameters? Physics often advances by turning accepted numbers into explained consequences. The Higgs field still carries numbers that feel like clues waiting for a deeper theory. Another puzzle is called naturalness, though the word should be handled carefully. It does not mean that nature must behave according to what humans find elegant. Nature is under no obligation to protect our preferences. Naturalness is a physicist's way of asking why some measured values are stable and not wildly different when all known effects are considered. The Higgs boson mass appears sensitive to influences from very high energies. If there are unknown particles or forces at higher scales, they might be expected to push the Higgs mass much higher unless something balances or protects it. The measured Higgs boson is not impossibly light, but it is light enough to make many physicists suspect that something deeper may be at work. For many years, supersymmetry was one of the favoured possible answers. It proposed a hidden relationship between matter particles and force particles, with partner particles balancing certain effects and helping stabilise the Higgs. It was a beautiful idea, and it remains important in theoretical physics, but experiments have not found the expected partner particles so far. That does not eliminate every possible version, but it has made the simplest expectations less likely. The Higgs remains where it is, looking standard model-like, while the protective mechanism many hoped for has not appeared. Composite Higgs theories offer another possibility. Perhaps the Higgs is not fundamental. Perhaps it is made of deeper ingredients bound by a new force. If so, the Higgs boson would be something like a proton in spirit, appearing as a single particle at accessible energies but hiding internal structure at smaller scales. Such an idea could explain why the Higgs has certain properties, but again, experiments have not yet shown evidence of compositeness. The Higgs behaves, within current precision, like a simple fundamental particle. There are also possibilities involving extra dimensions, hidden sectors, new symmetries, or fields connected to dark matter. Each idea tries to make sense of the Higgs by placing it into a larger picture. Perhaps the Higgs field is not alone. Perhaps it is one field among several. Perhaps the particle discovered in the collider is only the lightest member of a larger Higgs family. Perhaps hidden particles interact with the Higgs field so weakly that their effects have not yet been clearly seen. Perhaps the Higgs is a portal between known matter and a dark world that helps explain the missing mass inferred in galaxies. These possibilities are not established. They are paths being explored because the Higgs field sits in a place where new physics might reveal itself. The difficulty is that nature has so far been remarkably quiet. The Higgs boson was found, but not accompanied by obvious surprises. No clear new particles appeared beside it. No dramatic mismatch in its behaviour has forced a revision of the theory. This is scientifically valuable, but emotionally a little teasing. The standard model stands stronger than ever, while the reasons it cannot be complete remain just as strong. It does not explain dark matter. It does not include gravity as a quantum force. It does not explain why matter won over antimatter in the early universe. It does not fully explain neutrino masses. It does not explain the pattern of particle masses. It works beautifully, and it is incomplete. The Higgs field is therefore not merely a solved problem. It is one of the places where the incompleteness becomes visible. It is a confirmed part of the theory, but also a possible window beyond it. Physicists study the Higgs with great care because tiny deviations from standard model predictions could be the first hints of deeper structure. If the Higgs decays into certain particles slightly more or less often than expected, that could point to unknown particles affecting the process. If it sometimes decays invisibly, that could hint at dark matter or hidden sector particles. If its self-interaction differs from prediction, that could reshape our understanding of the Higgs field energy landscape in the early universe. The self-interaction is especially important. The Higgs field does not only interact with other fields, it also interacts with itself. This self-interaction helps determine the shape of the field's energy landscape, the way the field settled into its present vacuum state, and how that state behaved in the early universe. Measuring it is extremely difficult because it requires studying rare processes where more than one Higgs boson is produced. Current experiments are only beginning to approach this with enough sensitivity. Future colliders may improve the picture greatly. This matters because the early universe may have passed through a Higgs-related transition as it cooled. In the standard model, that transition seems too gentle to explain the dominance of matter over antimatter. But if the Higgs sector is larger than we know, or if new particles interact with it, the transition might have been stronger. Such a transition could have helped create conditions where matter survives slightly more than antimatter. That slight imbalance is everything. Without it, matter and antimatter would have annihilated almost completely, leaving a universe filled mostly with radiation and very little of the material needed for stars, planets, or listeners drifting towards sleep. So the Higgs field may be tied not only to why particles have mass, but to why there is matter at all. This is not proven, but it is a powerful possibility. It shows how one field can sit at the crossing point of many mysteries: mass, vacuum structure, early cosmic history, dark matter, matter-antimatter imbalance, and the search for physics beyond the standard model all pass near the Higgs. There is also the unsettling question of vacuum stability. The measured Higgs boson mass, together with the top quark mass and other details, suggests that our vacuum may be stable, or perhaps only metastable. Metastable means it could be long-lived but not the absolute lowest possible state. This should not be alarming. If the vacuum is metastable, its lifetime may be vastly longer than the current age of the universe. It is not something that should disturb anyone's sleep, but conceptually, it is extraordinary. Empty space may not be a simple final ground. It may be a state of the Higgs field that is stable enough for cosmic history, but not necessarily the deepest possible state in theory. This gives empty space a strange richness. We usually think of danger and change as belonging to objects, stars exploding, rocks falling, waves breaking, kettles boiling over because someone wandered off at exactly the wrong time. But in field theory, the vacuum itself has structure. It has a state. It has properties. Its stability depends on the fields that fill it. The Higgs field is central to that structure. What looks like nothing may be one of the most important things there is. And then gravity waits at the edge of the discussion. The Higgs field belongs to quantum field theory. Gravity, in our best current description, belongs to general relativity, where mass and energy shape space-time. These two frameworks are not yet joined into a complete quantum theory of gravity. The Higgs field gives mass to particles, and gravity responds to mass and energy, but the connection between the Higgs and gravity at the deepest level is not fully understood. Some theories suggest the Higgs field may have interacted with gravity in important ways in the early universe. Some even explore whether the Higgs could have played a role in cosmic inflation, the rapid early expansion of space. These ideas are intriguing but not confirmed. They show again how the Higgs field touches questions larger than its original purpose. The mystery beneath mass is therefore not one question, but a cluster of them. Why does the Higgs field exist? Why does it have a non-zero value in the vacuum? Why do particles couple to it with such different strengths? Why is the Higgs boson mass what it is? Is the Higgs field fundamental or composite? Is it alone or part of a family? Does it connect to dark matter? Did it influence the matter-antimatter imbalance? Does it tell us anything about the stability of the universe? Does it connect to gravity in a deeper theory? Each question is distinct, but all of them gather around the same quiet field. It is useful to remember how far we have already come. Mass once seemed like an obvious property of matter. Things were heavy because they were made of stuff. Then physics separated weight from mass. Weight became the pull of gravity. Mass became inertia and energy content. Then particle physics asked why elementary particles have rest mass at all. The Higgs field became the answer for many of them. But that answer did not make mass ordinary. It made mass more interesting. It showed that mass is not simply carried like a label. It can arise from a relationship between fields and the vacuum. That is a remarkable shift. The electron has mass not because it is a tiny hard object filled with heaviness, but because the electron field interacts with the Higgs field in a universe where the Higgs field has settled into a non-zero state. The weak force is short-ranged not because someone set its range by hand, but because its carriers became massive through the Higgs mechanism. Atoms exist with their familiar size and chemistry, because electrons and nuclei have the properties they do. Stars burn the way they do, partly because weak interactions proceed with their particular character. The Higgs field sits beneath these facts like a quiet agreement written into space. Still, the word beneath must not mislead us into imagining a physical basement under reality. The Higgs field is not buried below matter. It is not deeper in the sense of being farther away. It is present everywhere, including right here. The depth is conceptual. It belongs to explanation. It is beneath the familiar world because it helps explain the properties that the familiar world uses. The field is in the room, in the space between atoms, in the vacuum through which light moves, in distant galaxies, in the early universe's afterimage, and in the equations that have survived every test so far. There is a kind of humility in this. The world feels solid. A table feels like a table. A hand feels like a hand. A star feels far away and bright, yet solidity, touch, light, and starlight are all surface expressions of field behaviour. The Higgs field does not remove the reality of ordinary things. It explains part of why those things can be ordinary in the first place. A table remains a table, but now it is also a structure of atoms. Atoms are structures of particles and fields, and those particles carry masses shaped partly by an invisible field filling space. The everyday world does not shrink under physics, it becomes deeper. The unanswered questions give future experiments their purpose. The Large Hadron Collider continues to study the Higgs boson with increasing precision. Physicists look for rare decays, subtle differences, and signs of new particles. Proposed future colliders may act as Higgs factories, producing enormous numbers of Higgs bosons in cleaner conditions, so their properties can be measured with far greater accuracy. Other experiments search for dark matter, neutrino properties, gravitational waves from early universe transitions, and signs of new physics in precision measurements. The Higgs field may reveal its deeper nature through any of these routes, or it may remain stubbornly simple. If it remains simple, that too would be profound. A truly fundamental scalar field, with the exact properties measured, would be a basic feature of nature. It would mean the universe includes a field unlike the familiar directional fields of electromagnetism, a field whose vacuum value defines particle masses and helps shape the forces. That is already extraordinary. If deeper structure is found, the story becomes richer. Either way, the Higgs field is not a minor detail. It is a central clue to the architecture of reality. So what is the deep mystery still hiding beneath mass? It is the fact that mass, one of the most familiar aspects of the world, depends on something invisible and not fully explained. It is the fact that empty space has a field value that helps define particles. It is the fact that the standard model can describe the mechanism with stunning success while leaving the origin of its parameters unknown. It is the possibility that the Higgs field may be fundamental, and the equally tempting possibility that it is a sign of something deeper. It is the quiet gap between knowing how and knowing why. And here, at the edge of what is known, the mood of science becomes especially human. There is no need to pretend we have the final answer. The universe has allowed us to see far enough to discover the Higgs boson, far enough to confirm the field, far enough to understand why particles need it. But it has not yet told us everything. The next layer remains hidden, perhaps waiting in more precise measurements, perhaps at energies we have not reached, perhaps in cosmological clues written across the sky, perhaps in a theory not yet imagined. For now, the Higgs field remains both a foundation and a question. It helps make electrons, quarks, atoms, stars, chemistry, planets, and bodies possible, but its own deepest nature is still uncertain. It is not made of known matter. It may not be made of anything smaller at all, or it may be the visible surface of a deeper hidden world. The remarkable thing is that either answer would change how we understand reality. And so, as this slow journey through the Higgs field settles into its final quiet shape, we return to the room where we began. The air around you is made of atoms. The atoms contain electrons with mass from the Higgs field. The nuclei contain protons and neutrons, whose inner energies provide most of their mass, while quark masses still trace back to the same field. The light reaching your eyes is carried by massless photons, left massless through the structure of the Higgs mechanism. The warmth of stars, the chemistry of life, the solidity of ordinary things, and the hidden structure of empty space all meet in this one idea. Mass is not as simple as it feels. Matter is not as solid as it seems. Empty space is not as empty as it looks. And somewhere beneath the calm surface of the everyday world, the Higgs field remains present, silent, and unresolved, giving particles part of their identity while asking us, very gently, to keep wondering what identity means at the deepest level. If this quiet exploration has helped your thoughts soften or given you a peaceful path through one of physics' strangest ideas, then perhaps let the mystery rest beside you for a while, rather than trying to solve it all tonight. The universe will still be here in the morning, with its fields humming silently, its atoms holding together, its stars burning patiently, and its deepest questions waiting with the same calm patience they have had since the beginning. Sleep well, fellow traveller, wherever you are listening from, surrounded by matter, held by gravity, and quietly accompanied by the invisible field that helps the particles of the world become themselves,